let's get started. So welcome to the first event on blockchains plus X. So blockchains, as you know, as a source of decentralized trust, is forming the underlying infrastructure for a variety of applications, such as payments, decentralized finance, Web3, NFTs, and even cryptography protocols. So given how blockchains relate to such a wide variety of applications and to so many areas of computer science and economics, there's a lot to learn and understand about how this field evolves. So with Blockchains plus X, we'll conduct a series of workshops, each focusing on subset of topics. And today we are here with our first workshop, which focuses on the research and practice at the intersection of trusted execution environments, or TEEs, and blockchains. So trusted hardware, as we know, provides us with a source of trust rooted in hardware. And in the context of blockchains, they find several applications in the design of consensus protocols, mitigating MEV, and well, perhaps improving cryptography protocols. So we have a fantastic series of speakers today and tomorrow from academia and industry lined up to speak about some of these aspects. So here's what our program looks like for today and tomorrow. So in all, each of the days have 2 sessions each, and each session is about 1.5 hours long. So we'll have either 3 talks or 2 talks and a panel. So for each talk, the talk duration is going to be approximately 30 minutes. And, very roughly speaking, it's going to be split as 25 minutes of talking and maybe 5 minutes of questions towards the end. So in order to ask questions, given we are in the Zoom webinar environment, please raise your hand and, we'll let you ask the question by allowing you to speak. For async discussions, if you have, lingering questions after the talk, please feel free to use the Zoom Q&A to ask questions. And we also have a panel, so there's a panel today and a panel tomorrow. It's going to be for a short time of 30 minutes. But if there are questions that you think warrant a discussion with multiple speakers, multiple experts in the space, it would be ideal if we can discuss them in the panel. So we can have you ask questions right during the panel, but it may be easier for us to organize ourselves if you can, put in your questions at onlinequestions.org. And over there is an option for you to add new questions, as well as vote on existing questions. So that will give us a sense of priority of these questions. So again, the event ID over there, as soon as you visit the website, it will ask you for an event ID. And the event ID over there is 1235813. So it's very easy to remember that it's just the Fibonacci sequence. So with that, so since this is not my class, I'm not going to ask you if you have any questions before we move on. So I guess we'll just get started. So Natasha, do you want to maybe share your screen in the meanwhile? All right, our first speaker is Natasha Crooks, and she's a faculty at UC Berkeley, and she'll be presenting a talk on entrusted components we mostly trust. Over to you, Natasha.
Thanks. Can you hear me? Cool. This is the lack of Zoom issue is surprising, but thank you very much for having me. I'm excited to be here. So I'm going to be talking about why using trusted hardware to enable faster and more efficient BFT protocols is not necessarily a straightforward endeavor. And this is work that was led by Suyash Gupta, who is a postdoc at UC Berkeley. And if you have any questions after the talk, I would also encourage you to email him directly. So given I wasn't sure what the audience of the seminar would be and how early or late it would be for various people, let me give you a summary of my talk in one slide, and then you can either go back to bed or go to bed if time difference is hell. So the bad news is that I'm going to try and argue that trusted hardware, specifically trusted logs and trusted counters, cannot be used to efficiently reduce replication factor to 2f+1 of most BFT protocols. The good news is that I'm going to also argue that trusted hardware can be used to design more scalable and efficient BFT protocols when one uses 3f+1 as a replication factor. So most blockchain systems at their core use a BFT replicated state machine. So what is a state machine? Well, it's a client that sends a request to a magic black box that then sends it a response. This magic black box is guaranteed to remain safe and live in the presence of arbitrary failures. Safety here means that this black box or the execution remains equivalent to a linearizable execution, so an execution in which there's a single machine and no concurrency. And live means that the Bob here will eventually obtain a response to its request. Now, internally, replicated state machines use a consensus protocol. So consensus protocol assumes a number of replicas, up to f of which can be malicious, and in effect tries to consistently order a log of operations at all replicas. In the rest of the talk, I'm going to assume the partial synchrony model. So very standard up to now. Now, intuitively, you can break down a consensus protocol, BFT consensus protocol, into a sequence of phases. You have little Bob here that sends a request for a transaction, say T1, to a bunch of replicas. Here we're going to assume that replica 1 is the leader, so I'm going to talk about leader-based systems. This leader is going to forward its request to the rest of replicas, and that request is going to go through a non-equivocation phase. So at a very high level, this guarantees that no two requests will be within this particular reign of a leader proposed, also validated at the same log number. We're going to say that the request is prepared. In a persistence phase, we're going to guarantee that this transaction at that particular log number is going to be preserved across views. That means if the leader for some reason dies and a new leader is elected, that request is going to be preserved. At that point, we say that the request is committed. Once the request is committed, we can then execute the request. And this is something that a lot of papers tend to forget, the execution phase. And the reason why that's going to be important is that little Bob here, once it gets confirmation that the request has been committed, it also wants to obtain the result of its request, the response. And it needs to somehow validate that the response it is getting, in this case, banana, is actually a correct response. So let's go into a little bit more detail in each phase. So like I said, the non-equivocation phase has as its primary task to create a prepare quorum. We're going to guarantee that no two prepare quorums can exist for the same transaction at the same slot. The way that we do this is to ensure that every quorum needs to intersect in at least one honest replica. Why honest? Because a replica, if every quorum intersects as one honest replica, then this replica is not going to vote for two quorums that conflict, and so we know that the invariant is going to be preserved. So if you have our replicas here and replicas, we know that, or we can prove that our quorums need to be of size n plus f plus 1 over 2, such that we guarantee that all the quorums will intersect in at least f plus 1 replicas, and f plus 1 intersecting in f plus 1 replicas means that at least one of those is honest, because we only have f replicas. Now, using this derivation, we can also show that the minimum number of replicas that we need when we can have equivocation is 3f plus 1. The persistent phase, like I said, guarantees that when we do elect a new leader, we must ensure that any committed operation is going to persist across views. Now, because the persistent phase isn't particularly relevant for my talk, I'm not going to go into any more detail now. The execution phase, on the other hand, is, I'd say, the forgotten child of a lot of consensus papers. And it must enforce two things. So the first one, it must guarantee that the request, when the client receives a response, the request has to have been committed. So usually we use some form of commit certificate for that. using signatures, threshold signatures, max, you name it. But we're going to say that the request is committed and the client can verify this. But we also need to guarantee a mechanism by which the client can ensure that the result of the executed request is also correct. So if I read key X, I send my read through the RSM, I want to make sure that the result I'm getting, say banana, is in fact the result that I should have read. Because what could happen is a Byzantine replica tells me, you just read apple, and here's a commit certificate. Great. I have no way to determine whether apple is in fact the correct result. So because of that, it's important to highlight and emphasize that a commit certificate isn't enough for a client. We also want the client to receive F+1 matching responses. So again, as an example, little Bob here must not just receive a commit certificate, but must receive a F+1 times. If little Bob here receives a F+1 times, we know that at least one honest replica said the answer was A, and thus we can trust that value. So if we're all here, we all think the BFT is cool, but not everyone agrees. And not everyone agrees because most crash fault tolerant systems require only 2 F+1 replicas. In contrast, BFT fault tolerant systems require at least 3 F+1 replicas. So there's both a performance cost, but also a managerial cost in that you now have to maintain and manage F extra machines. And the root cause for why we need this extra replication factor in a BFT system is equivocation. It's this idea that your quorums need to intersect in at least F+1 replicas as a way to preclude a Byzantine replica from lying and sending different messages to different people. So can trusted hardware save the day? Well, trusted hardware, and here I'm going to be specifically talking about trusted counters and trusted logs, became very popular a few years ago, about 10 or so years ago, because it provided a mechanism to attest the order of each transaction such that replicas could not equivocate. There was a long line of research in this, A2M, Turing, MinBFT, MinZiziva, recently Hot Stuff, and Demesis. All of these use trusted hardware and trusted counters and trusted logs specifically in order to preclude equivocation and thus to reduce the replication factor. So we're done. I've told you how trusted hardware is fantastic, and we can all move on to the next talk. But obviously that's not quite true, right? For the rest of this talk, I'm going to try and convince you that the situation is a lot more subtle than that. And specifically, we identified 3 limitations with existing trust BFT protocols that actually led many of them to have worse performance than the traditional BFT system. So the first one is limited responsiveness. I'm going to try and convince you that there are executions in which the client is unable to obtain a response to its request without changes to the protocol. So as a reminder, this is what your abstract BFT protocol system looks like. And I'm intentionally staying abstract here because these are issues that are common to almost all the existing BFT protocols that we saw. So because we only have 2 F+1 replicas, this means that in order to prepare a request, we need to obtain F+1 replicas to vote prepare. We then need to obtain F+1 replicas to vote commit. And finally, we also continue to require F+1 replicas to reply to the client in order to validate the integrity of the response. That hasn't changed. So what could go wrong? Well, let's assume that our primary is Byzantine and sends its operation only to itself and to one other replica. So in the example here, you have the 2 top replicas that receive the request. Now, in the next phase, these replicas are going to exchange messages in some way. And I'm intentionally not specifying what that way is because it doesn't matter. And we're also going to assume that messages to the last replica are delayed by an amount that is greater than the view change timeout. So great, the request is now committed, right? Remember that our quorums now are f+1. So we now have a commit certificate. So from the narrow point of view of the consensus protocol, we haven't violated liveness. Our operation is committed. Unfortunately, we now only have f+1 replicas that know about the operation. And so if one of those is Byzantine, namely the leader, it's not going to reply to the client. So the client is not guaranteed to always receive f+1 matching responses. And this cannot validate the integrity of the request. And that's one of the main things we want to highlight, is that using these smaller quorums does not necessarily guarantee that you will therefore have sufficient responses for the client to actually be able to consider the request as completed. The request will be committed, but from the point of view of the client, it won't be completed. So usually at that point we say, okay, well, eventually those messages are going to arrive, or there's going to be a view change triggered. So, let's have the replica complain. Something's fishy here. I'm not getting anything. Let me trigger a view change. Unfortunately, in order to trigger a view change, you have to have f+1 people. Otherwise, Byzantine replicas could cause spurious view changes. And here we only have one replica complaining about the state of the system. So eventually, the messages are going to arrive. So are we done then? Well, not really, because now that the replica has started a view change, it cannot accept requests from a lower view. So again, we're stuck. So one point that I want to emphasize here is not that there are no way to address the situation. You could imagine the client broadcasting the commit certificate. You could imagine the final replicas always broadcasting the commit certificate. Or at checkpointing, some of these replicas will eventually learn about the committed request. But all of these add latency, add communication, and thus have the consequence of removing some of the benefit that we had from the original BFT protocol, because there's now an extra phase, or there's now an extra communication round, or you're now progressing at the speed of your checkpointing algorithm. So the second limitation that we notice is the lack of parallelism. So because every message sent requires an attestation that is bound to a specific sequence number, replicas cannot process transactions in parallel out of order. And this is one of the ways in which PBFT achieves very high throughput. The ability to be bound, not by the latency of phases, but by the resources available in your system, such that you can concurrently process transaction T1, T2, T3, T4, T5, potentially even committing T5 before you've committed T1, and then obviously executing them in order. And so because of that, we notice that most of the Trust BFT protocols that we identify, so A2M, Turing, and so on, actually achieved lower throughput than our PBFT implementation. And this was especially the case when you went to the wide area network. And finally, something that we tend to all intentionally ignore, and it's not going to come as a surprise to many of you, but it's rollbacks. Most trusted counters implementations right now are using SGX or some equivalent. And we know that if you have the presence of rollback, then the system, you can trigger this equivocation in the system. So you lose this guarantee of non-equivocation. Now, there are ways to address this using TPMs or persistent counters, but these implementations are still today prohibitively expensive. And this is especially bad because existing implementations of BFT, of Trust BFT protocols, require an attestation almost for every message, not just the primary, for every message. And so we ran this small simulation where we increased the latency simulated the latency of accessing a trusted counter that actually wasn't subject to rollback attacks, and measured the impact on throughput. So this is using F = 32, and MIMBFT is a protocol from 2013 that leverages trusted hardware, but the results are the same for other protocols. And what you see is that while we get pretty good performance with MinBFT 39K, and that's roughly the same as PBFT, the second you go to 10, 30, 100 milliseconds, performance starts to crater. And we actually are unable to get more than 500 transactions per second for a simulated cost of 200 milliseconds to accessing the trusted counter. Now you might say, well, 200 milliseconds is excessive, but actually it turns out that SGX persistent counters have a latency of access of approximately 187 milliseconds. So again, this is not to say that we can't use trusted hardware. This is to say that currently existing implementations, if you want to deploy them and worry about things like rollback attacks, the performance of trusted hardware isn't there yet. So we do. Well, we tried to propose a way forward. And the way forward that we propose is to go back to 3F+1 replicas. One of the arguments there is that resource overhead is measured in terms of throughput loss. If you can achieve higher throughput per replica at a replication of 3F+1 than you could with 2F+1, then use 3F+1. You do still have additional managerial overhead, but still, what you care about is throughput per machine. It's not just the number of machines or the throughput number. So by returning to 3F+1, you can actually really harness the power of trusted hardware. And trusted hardware becomes useful to both reduce the number of phases, for example, shaving a phase off PBFT, and also reducing the communication cost, for example, ensuring linear communication costs instead of quadratic communication costs. So in a little bit more detail, the main properties of our suite of FlexiTrust protocols are the ability to use a trusted counter at the primary only, and this is especially important right now, given accessing a persistent counter is so expensive. The ability to support parallel consensus invocations, which we I tried to convince you is important for throughput. To mitigate the responsiveness issue without having to involve the client and without having to sort of rebroadcast commit certificates. And finally, reducing the number of phases compared to BFT protocols that do not leverage trusted hardware. So I won't go into the details of the protocols. This is one of the many pleasures you'll have if I've convinced you to read our paper. However, I want to give you a brief idea of performance. So here we compared several existing BFT protocols that use trusted hardware, so PBFT EA, so that's A2M, MinBFT, MinZiva, to our, including in PBFT as well, to our own implementation of FlexiBFT and FlexiZiva. And so what you see is that we're able to obtain significantly higher throughput than the existing systems, 160K for FlexiZiva compared to about 85K for MinZiva, which is a 2F+1 equivalent. And we're able to do this because of the fact that we support parallel consensus invocations and because of the fact that we reduce the pressure on the trusted hardware by accessing it only at the primary. So with that, I tried to convince you that existing BFT protocols, when they use trusted hardware, have always tried to do so as a way to reduce replication factor. But that is not as easy as we think. This introduces responsiveness issues when you consider replication state machine. This means that you cannot support parallel consensus invocations. And it also means that you need to invoke trusted hardware on every request and specifically at every replica, which is not currently something that you can do given current technology. In contrast, our new protocol suite, FlexiTrust protocols, by biting the bullet and going back to 3F+1, can nicely address the parallel consensus invocation issue and the responsiveness issue while for now mitigating the associated cost of invoking trusted hardware at every replica and for every request. So with that, I'm happy to take any questions. This is work that's going to appear at Eurosys in a couple of weeks. And this was work that was led by Suyash Gupta. So any mistake is mine in this talk, and the talent is all his. With that, thank you very much, and I'll be happy to take any questions.
All right. Thanks, Natasha. Thanks, Suyash. So are there any questions? So among the attendees, I'll repeat again. So feel free to raise your hand if you have a question, and we can let you ask the question.
Aniket?
Yeah, okay. So I wanted to make sure that this. So very interesting talk and take in general. So I have a question regarding how to look at the systems, and I'll start. My question is related to like very basic, like how we set the system. You the way I understand, you start that, oh, I want to tolerate F failures. And in such a system, I will require a BFT protocol required 3F plus one party. So let's say my F is 10, then my BFT protocol will require 31, while the other protocol will require 21. If you use counter and go for such approach. That's one way to look at it. There is another way to look at it is that I start with 31 nodes, and I know that I can tolerate 1/3 failures there. And now my question will be, I have again same 31 nodes, and I have a protocol which can tolerate 15 failures if I just go like that. But let's say I want to provide the same failure rate. Maybe I can just go for some kind of a random selection, and I go for much fewer nodes. And this can be following some like hypergeometric distribution whatsoever. And the number of nodes that could be employed in that case could be smaller. So my question is that maybe if we go from that approach where we start with the entire system of nodes and select a committee among them, things may look slightly different in terms of performance. So just a thought, but I'll be happy to explain that more on a call.
So I might be responding completely. So one, I think it's an interesting node selection. I think is an interesting point of research, and we should be looking at it a lot more. And I know you have. I know people at OmniLedger has, and so on. I think there is a question of whether throughput is the right metric. So we asserted that what you cared about was throughput per machine, and that you had the extra nodes. But as you point out, if you have a fixed set of nodes, then how can you use trusted hardware to tolerate the highest rate of corruption, almost independent of cost? Independent, quote, is another way to look at it. And at that point, I think the existing systems that are there, and while they might perform worse than the 3F plus one counterparts, do tolerate a higher corruption threshold and can be modified in order to address the responsiveness issue that we mentioned and so on. So I guess I think you're right. I agree, and I think it points to two ways of looking at it. One is what's the highest threshold of corruption that I can tolerate, and cost is almost irrelevant. Well, cost is a secondary concern. The primary concern is safety under the highest corruption rate, and second, it's what's the best throughput that I can achieve. And probably different circumstances will require different, will prefer different approach.
Yeah, so also I had another part to question, but let me write that in a detailed email. Let's give the
Sounds good.
Yeah.
So there are a couple of questions on Q&A. Mark, so do you want to maybe ask your question over here, or I can read it for you?
Sure, I hope you can understand me. Sorry, I'm on the phone in the car. So I have a question concerning the use of trusted hardware. You said that in your Flexi approach, only the primary uses the trusted hardware. But isn't it the case that in MinBFT, only the primary uses its USIC in a view?
So to the extent that I remember it correctly, the commit and the prepare messages also need a call to this create UI API that they have. So I don't think that's the case. I think the prepare and the commit also need to invoke the they needed this UI number that they have as a way to prevent dependency.
You're right. You're absolutely right. I forgot about the commit messages. Sorry. Yeah.
You had me scared for a second.
All right, thanks, Mark. Arvind, do you want to go next?
Sure. Right. So it's a probably a basic question. So could you just clarify the model a bit as to who in the protocol has access to the trusted hardware, and if you can tolerate some relaxation to it, like maybe tolerate the same guarantees if some of the nodes don't have access to this hardware? Or, yeah, it's just a very basic question.
So I think because most BFT protocols assume a sort of symmetric view of the world where each replica can eventually become the primary, we assume that each replica has access to trusted hardware. And even though in our FlexiTrust protocols, we only invoke trusted hardware once at the primary, this does not mean that other replicas don't have access to trusted hardware. It means that they don't use it. I think it would be interesting to consider a heterogeneous model where some nodes have access to such trusted hardware and thus can provide proof that they did not equivocate, and other nodes don't have access to trusted hardware and thus likely require either a larger quorum size or an extra phase. And I think looking at the interaction between the two would be super interesting.
Yeah, thanks.
I think this actually speaks to a lot of heterogeneous failure models that people have started looking at. Depending on how much trust I place in a node, I may consider that it behaves differently, and trying to consider different quorums when I think some of the work at Stellar also looked at something similar, where you basically, depending on who you trust, you require larger or smaller quorum sizes. And then these quorums somehow have to talk to each other in a happy family eventually.
Thanks.
Thanks, Arvind. Itai, go ahead.
Yeah, and Natasha, I wonder if you could say a few words about how to do parallel consensus, and how do you make sure they maintain the persistency of these events?
Sorry, I'm not entirely sure I followed your question.
How do you, I mean, you said that one of the things that increase performance is to allow parallel consensus.
Mm-hmm.
And so I guess if you have one counter, it's easy to have a rollback protection. So I'm just wondering, how do you kind of get parallel counters and good rollback protection together?
So we don't consider rollback protection. Because none of the other systems considered rollbacks, we also did not, and so we would require the same performance. So we are not subject to rollback attacks, assuming that we use TPMs and persistent counters. Without that assumption, we are subject to rollback attacks in the same way as A2M, Mises, and so on. If they're implemented using SGX, are also subject to rollback attacks. What we do consider is, in the absence of rollbacks, because we have the larger quorums again of 2f+1, this is what enables us to not have to use an attestation at the replicas, and we only need it at the primary. Does that answer your question?
Yeah, thank you.
So finally, I have a couple of questions as well. I think the first one is, you mentioned that there is this notion of responsiveness where the client needs to hear from F+1 parties versus, receiving one certificate. I think the question is, I mean, I don't entirely understand why one certificate does not suffice, because at the end of the day, if you have F+1 such responses, this one party can collect all of these responses, assuming they're signed, and send it to the client. and that is effectively responses from F+1 different parties, right? So I think so that is the first one. And the second is, I'm trying to get a sense of, how trusted hardware helps in this entire process. And part of this is, recently we were thinking about this problem on getting two phases with quadratic communication and responsiveness with hot stuff too. And at least at the face of it, it appears, we get similar properties. So I'm trying to get a sense of, what trusted hardware gives you in addition. So I totally understand this is very new and I haven't compared it myself. So maybe I'm missing something basic out there.
I think you're right that once you have the existence of a commit certificate, you can assign a temporary leader, and it can collect those certificates and it can broadcast them to other replicas in such a way that you will eventually get F+1. This is not what existing protocols do, so you have to worry about that. But it also adds latency. It's an extra phase. If that leader is malicious, then you have to try again. And so our point wasn't that you couldn't do it. Our point is that if you wanted to guarantee that you will get F+1, then you may have to suffer an extra phase or have to do an extra round broadcast in order to. And so I think it was, and that comes at a cost. And this comes especially at a cost because one of the arguments that, for example, MinBFT makes is that you can shave a phase, or you can achieve lower latency. So I think our point was very much not that there wasn't not a way to address it, but that this way would come at the cost of either an extra communication phase, extra signature verifications, or at the cost of processing at the speed of your checkpoint algorithm. As it relates to two phases and hot stuff, I haven't read your latest paper. I've seen it appear in multiple places on my feed, but it's on my to-do list, and so I'm not yet able to answer this.
Sounds good.
So I'm happy to talk offline. I haven't seen the result.
we can chat
I haven't read it yet, so I can't answer this.
No, we can chat offline. All right, Natasha, we've grilled you enough. Thank you so much for the amazing talk. And I think that maybe let's move on to the next talk. Heidi, do you want to share your screen?
Yep, give me 1 second. Does that look okay?
Yep. So thanks, Heidi. So our next speaker is Heidi Harvard. And so she's from Microsoft Research, and she's going to be talking about confidential consortium framework building secure multi-party services in the cloud without handing over the keys to the kingdom.
Thank you. I made it slightly more difficult for you by slightly changing the title when I wrote the slides from when I submitted it. But yes, as Kartik said, today I'm going to be talking about the Confidential Consortium Framework, which we refer to as CCF. It's just a short talk, so I'm going to pick a couple of features of CCF. These are the features that are most exciting to me and that I thought might be most interesting to an audience of people who choose to attend a workshop about the intersection between blockchains and TEs. But there is so much to CCF, and so I really would encourage everybody to have a look at CCF for themselves on the ccf.dev website, or you can go onto GitHub and go /Microsoft/CCF to learn more broadly about the stuff that we're doing and not just my particular highlights for this talk. So when I sat down to write this talk, the first question that came to my mind, following on from the Twitter thread that started this workshop initially, was this question of how we can leverage TEs to build better blockchains. And that sounds nice, but it's very, very vague. So what does it mean for us to make blockchains better? Well, we could mean improving performance. It could mean, for instance, higher throughput or lower latency. It could mean us trying to make blockchains more efficient. As Natasha was discussing, there's been efforts to kind of reduce from a 3F+1 view of the world to a 2f+1 view of the world? Can we therefore make them more environmentally friendly? Can we make them cheaper? Can we improve the safety guarantees that we get from these systems? Can we perhaps change the threshold of how many nodes need to be well behaved for us to get safety or liveness, or can we remove that entirely? So that's the first kind of question that came to my mind when I was thinking about preparing this talk. But then as I thought about it a little bit more, I thought of this quote, this traditional quote that's like, ask not what you can do for your country, but what your country can do for you. And so I kind of rewrote it for this workshop and said, my fellow researchers, ask not what TEs can do for your blockchains, ask what blockchains can do for your TEs. And so this leads us to the second question I wanted to reflect on today, which is how can we leverage blockchains to build better systems on top of trusted execution environments? Because whilst trusted execution environments give us neat properties like confidentiality and integrity during execution, they unfortunately do not solve all of our problems for us. For instance, these properties are limited to a single node. So there's the question of how do you build a distributed system? How do you get these different nodes with these TEs to establish trust in one another? And what about persistent storage? Natasha talked quite a bit about kind of rollback attacks and how do we handle these? So what I'm going to do now is tell you a little bit more about CCF, and then I'm going to revisit these questions later. But before that, big caveat in this talk, because I could talk for many hours about CCF and then the assumptions we make of trusted execution environments. But since I only have a short while, I'm going to assume that TEs are worthy of our trust and then roll with that assumption and see what systems we can build. But if you're interested in kind of the post-compromise story and stuff of CCF, we do have some interesting answers. So I'm happy to discuss that a bit later. So for those of you who know me before I joined Microsoft, I'm very much your traditional distributed systems person. So as a distributed systems person, I love a good 3 or 4 letter acronym, whether it's the CAP theorem, FLP, ACID, BASE. So when I joined Microsoft, I joined the confidential computing group at Microsoft Research Cambridge, and I was like, what do I know about confidentiality and privacy and security? And I was like, I remember there was a 3-letter acronym in my information security course when I was an undergrad, and that's CIA. And that's what I'm going to use today, although putting my distributed systems hat on, I'm going to slightly modify the standard definitions. So confidentiality, integrity protection, and high availability are 3 properties that we clearly want to have in our systems. Nobody ever says to me, oh, Heidi, my system is just too fault tolerant, right? This is not something that happens. So I think it's very clear, and we can talk about why it's important that data is confidential and why it should be integrity protected and why it should be available to us when we need it. But I think it's pretty uncontroversial to say that these are 3 really important properties that we would like to achieve simultaneously. As I mentioned, this was something I came across in my undergrad, and even then this was kind of old news. So why am I talking about it today? Like we've solved these problems. Well, unfortunately, reality is messy and painful. In practice, achieving these 3 properties is surprisingly difficult. And this has been made much more difficult by 2 factors. The first of which is cloud computing. So cloud computing in many ways is amazing. It gives us the capability to build systems that can scale globally really easily. We don't have the stress and the work of managing machines, all that good stuff that's led to this mass migration to the cloud. Unfortunately, it does mean that you're fundamentally building your systems on top of untrusted infrastructure. You no longer have physical access to your machines and not even control over the kind of software stack up until the point when your software starts. And it's not just cloud computing that makes achieving CIA tricky. It's also the growing demand for multi-party services. So as digital systems become increasingly integrated in our lives, we want to be able to collaborate and compute over shared data sets, even when organizations don't necessarily trust one another. Now, this wouldn't be a blockchain talk if I didn't have an example with some banks in. So here we go. Consider a scenario where we have 2 different banks, the green bank and the yellow bank, because I'm not very good at naming things. And we have a financial regulator, And the financial regulator wants to determine who, as in which customers, have more than $2 signs across both banks. And there's two options for how we could do this. The first option is that the financial regulator asks each bank, can you send me the names of the customers who have strictly more than $2 signs worth in their accounts with you? Each of the banks can compute this and then return the result back to the regulator. The advantage of this is that it's good for customer privacy because the data never ends up anywhere that it doesn't need to be. So the financial regulator only finds out about the balances of these kind of high net worth individuals. But the cons are that the result is actually incomplete. So if you look at the example here, the green bank would send to the regulator that Alice has more than this set amount of funds, and the yellow bank would say neither of my customers have more than this amount of funds. But you can see that this is incomplete because actually across the two banks, Bob has more than strictly more than $2 signs worth in his accounts. So the other way that we could do this is we can have the banks send all the customer data to the regulator, and the regulator could do this computation locally. This has the advantage that you get a complete result, but the disadvantage that it's bad for customer privacy. For instance, the regulator finds out that poor Charlie only has a $1 sign. So it would be absolutely amazing if we had a general purpose foundation on which we could build trustworthy multi-party systems on top of untrusted infrastructure, so we can solve problems like the one I just showed time and time again. And to break that down a bit, by general purpose, it would be useful for us to have one solution that's suitable for a wide range of applications. This means it needs to be able to support state, it needs to be long running, it needs to be flexible, it needs to support standard programming languages, it needs to have decent performance, it needs to have all that good stuff. And we want to be building trustworthy services, so we're going to at least need to have these three properties: confidentiality, integrity, and high availability. And we want these to work in a multi-party scenario where we've got different parties who want to govern and use the service. So, can we solve this problem? And the answer is yes, we can, with yet another three-letter acronym. There's a theme to this talk, and that is CCF. So CCF is an overview of CCF is given in this figure here, and I think the most important thing that you need to understand in order to understand what's going on with CCF is that CCF decouples these two roles that are often combined in traditional blockchain systems. So it separates out the operators. So these are the parties who are responsible for managing the infrastructure. So in our case, this is usually like a cloud provider, from the consortium members. So this is a set, not just one party, but a set of parties who are responsible for overseeing the service. And there's also the users of the service. And so you've got these three distinct roles in the system, and then you have a CCF network that is made up of a collection of CCF nodes. So how does CCF work? Well, conveniently for this particular workshop, it leverages trusted execution environments. So by using TEs, CCF is able to achieve data confidentiality and execution integrity, even when it's running on untrusted cloud infrastructure. And secondly, extra convenient for this workshop, it leverages an immutable ledger from which it is able to provide data integrity and high availability and transparent multi-party governance. Now, this is a simple story. In practice, the reality is that these two things are actually really tightly intertwined. We're only able to provide confidentiality from our TEs because of the ledger that's in CCF, and vice versa. The ledger is only able to provide high availability because of the TEs as well. So let's dive in and have a look at how CCF actually works. So there's four main components of a CCF node. First, and most important, you've got the application logic. So CCF is a framework, so you can bring your own application with you. So if your application is maybe the banking application that I showed, maybe you want a privacy-preserving voting system, maybe you want a distributed logging application or a COVID tracing service, whatever it is, you bring your application logic to CCF, and your application logic can store state in a transactional key value store that's provided by CCF, and the key value store state is maintained by an immutable distributed ledger. And we have a custom crash fault tolerant consensus protocol that reaches consistency on that ledger across that set of nodes. So those of you who knew my work before I came to Microsoft, I'm very much classic consensus, crash fault tolerant, Paxos, Raft kind of person. So distributed consensus 101, a tale of older time. We get two F+1 nodes and we combine them together to get high availability by basically having users submit requests to a primary. The primary executes that request. The resulting transaction is put into the primary's ledger. That is then replicated to the backups. And once the majority of nodes have a copy of that, we consider it to be committed. If the primary fails, then we have an election, which will involve a majority of nodes again, and a new primary will take over. So this is how we can achieve the A in CIA. And this is a neat story, which many of us are very familiar with. But just because it's a nice story, doesn't necessarily make it true. So remember that CCF wants to separate operators, so those who are in control of the nodes, from the consortium members. That means we don't trust the hosts that are actually running the CCF nodes. So how is this going to actually work in practice? Well, we do have TEs, so we can run the CCF nodes inside of trusted execution environments. Trusted execution environments give us nice properties like memory encryption. But if it was that simple, this would be a short talk and frankly a short workshop. One of the key issues we face, and this is something that Natasha picked up on in her talk, is the problem with persistent storage. So we need persistent storage, both because memory is limited and also because it's volatile. But persistent storage lies outside of our trust boundary. So we're going to have to do a bit of work to get this classic crash fault tolerant consensus algorithm to work in an untrusted environment. So the first problem that we need to solve is confidentiality. So we need to add confidentiality to the ledger. The transactions in the ledger in CCF can be public or private, and so we simply encrypt the private transactions in the ledger using a shared ledger secret before they're being written to the ledger. That's simple right now. We'll revisit it a bit later. So step 2 is going to be, how do we add integrity protection to the ledger? And CCF does this by maintaining a Merkle tree over the ledger. And the primary periodically signs the root of the Merkle tree using a signature transaction. This means that checking that the signature transaction ensures the integrity of the ledger up to this point. So in the diagram here, we can see a ledger at the bottom with some transaction IDs in, and we can see the Merkle tree, and the root of the Merkle tree is signed by the primary and put into this special transaction. And this ensures the integrity of the ledger. So at this point, we've got confidentiality, we've got integrity, but we haven't solved the problem of rollback attacks. So malicious hosts might not be able to read private transactions or corrupt the state of the ledger, but they could truncate it. So we have these periodic signatures, but malicious hosts could roll back the ledger. As Natasha also mentioned, many TE systems do try to prevent this. So they might use TPMs or they might use distributed monotonic counters to try to ensure that there isn't a rollback attack. But in CCF, we took a different approach. CCF embraces rollback attacks. So it just assumes that the state that's on disk, when you read from it, those things that are returned just might be stale. And so we have to deal with that, but we don't try to fight it. One result of this is that CCF has to treat nodes as basically being ephemeral. When a CCF node dies, that's it. As far as CCF is concerned, if you want to participate in the system, we're going to have to go through a reconfiguration to bring you back into the network, because we're not just going to trust you if you restart from persistent storage, because you may be behind. So reconfiguration is a topic that is very often overlooked in the academic literature, but it's vital for any consensus-based system, and it's even more important for a system like CCF, where we say that we don't trust our persistent storage, and therefore we don't allow nodes to just crash and restart without going through reconfiguration. CCF uses a novel horizontal reconfiguration algorithm where there's a special reconfiguration transaction that's added to the ledger, which allows CCF to atomically change in a single transaction from one configuration to another. This works really nicely, except for the fact that the reconfiguration therefore depends on our ability to achieve consensus. This means if more than F nodes fail at the same time, we've now got ourselves in a spot of trouble because we can't reconfigure to replace those nodes or to kick them out of the system. And this is where disaster recovery comes in. Disaster recovery, again, is often overlooked by the academic literature, but it's vital for systems in practice, and particularly a system like CCF. So disaster recovery is a protocol by which we can restart a CCF service if some catastrophic failure was to happen. We could even restart a CCF service from just a single copy of the ledger. Unfortunately, in this case, we can't guarantee that the service hasn't been rolled back, but we can guarantee that we'll restore it back to a valid state. So the way that this works is we take advantage of the fact that CCF had its own solution for providing encryption on the ledger with this ledger secret. The consortium members have essentially recovery shares, and if enough of them come back together, we're able to recover the ledger secret and then restart a service from the ledger. So far, I focused on the CIA aspect, particularly on how we can achieve CIA on untrusted infrastructure. But what about this multi-party support? So the CCF consortium members are responsible for overseeing the CCF service. So I just mentioned they're responsible for signing off on disaster recovery, but they're also responsible for agreeing things like what application logic is actually running, how do you upgrade it, when is it safe to do so, who are the users of the system, who are the consortium members of the system, when can we open a new network after a disaster recovery, or when can we allow a new node to join. So in order to do this in a multi-party setting, we have a governance procedure whereby consortium members, in order to take an action, they will submit a governance proposal, which is essentially a special transaction on the ledger, and then other members come along and they submit ballots, either voting for or against that governance action. And then the governance action is taken if a consortium of members agree that it's okay to do so. This behavior is also completely configurable. So remember that CCF wants to support as many applications as possible. So we want to support applications with kind of custom ideas of how to vote for when governance actions can happen. So every CCF application can use its own programmable constitution describing the possible governance actions and their voting rules. The constitution is provided when you start up a CCF system, and it can even be updated at runtime with a governance action. I mentioned earlier that the transactions on the CCF ledger can either be private or public, and this is really where the public transactions become useful, because governance proposals and actions are recorded as public transactions, and this means it's much easier for us to check the ledger and to account for what's gone on in the system so far. So that is a few highlights from CCF and a few of my favorite picks. So thinking back to the research questions that we started with, can we leverage trusted execution environments to build better blockchains? I believe the answer to be is yes, absolutely. CCF combines decentralized trust with centralized cloud computing by fundamentally decoupling operators and consortium members. So this means that you can run CCF on completely untrusted infrastructure. So this is different from kind of traditional blockchains where we assume that each party runs their own node, and that therefore we need a certain amount of decentralization, and we're not assuming that enough people will collaborate that we'll get past this threshold when we can no longer guarantee safety. Instead, CCF says you can run your own node if you want, but otherwise you could run it in the cloud if you wanted to. And looking at question 2, can we leverage blockchains to build better systems on top of trusted execution environments? And the answer is yes, absolutely we can. The immutable ledger inside CCF not only keeps track of how data's changed over time, but it's also used for Multi-party governance is also used for various other purposes I didn't get to talk about today. So it's used for recording who's trusted, whose attestation has been checked, etc., etc. So it's been absolutely invaluable when it comes to building systems on top of TEs. So in conclusion, CCF provides a general purpose foundation for building trustworthy multi-party services, even when you're running on untrusted cloud infrastructure. I only had time to talk about a couple of features of CCF, but there is so much more that I didn't have a chance to talk about. CCF provides verifiable receipts to users so that they can check that their transaction has been committed and that they can then share this receipt with other parties. CCF has support for read-only transactions on a fast path. CCF provides solid performance numbers. We have snapshotting, indexing, historical queries. We're doing some interesting work with like formal specification and model checking using TLA+. There's so many different components of CCF. And part of why CCF has all of this is because we are using CCF in production. So CCF is utilized in the Azure Confidential Ledger, and it is an open source project that you can check out today at github.com/Microsoft/CCF. So that's it for me, and I welcome your questions.
All right. Thank you so much, Heidi, for the amazing talk. So we can open the floor for questions. So there's already one written up on the Zoom Q&A, and since this is from an anonymous attendee, let me read it out. So the question says, how is the ledger secret generated? Is it that all consortium members perform a DKG and get their share? And is it for a T of N, for T less than N secret sharing? And does the T vary based on how you encode the governance rule?
Okay, yeah, sorry, I've just managed to pull up the question myself. So yes, it is a T of N. So the consortium members, say you have N consortium members, you don't necessarily need all N to come and sign off on a disaster recovery. You have a threshold, in this case it's called, they've called it T, and you only need up to T. T is completely customizable, and T is also changeable via a governance proposal. So T is stored inside the key value store underneath CCF. So this is one of the things that I really like about CCF, is that the key value store that I talk very much as being like, oh, this is where applications store their state, is also where CCF stores all of its state. So that is where CCF actually keeps the ledger secret, which is encrypted using the ledger secret wrapping key, and that is what's decoded with the recovery shares, but it's also where it keeps things like the T.
Thanks, Heidi. So I guess Suyash had his hand up. Suyash, do you want to go next?
Yes, thank you for the presentation, Heidi. So I had two quick questions. One,
Yep.
If CCF is using a consortium, then how is it providing privacy in the traditional setting? Because the consortium members would be inherently knowing all the transactions. The example which you showed initially to us was that there are two banks, and if they exchange information with each other, then the information will be revealed. But now in this case, consortium members will know all the information. And my second question will be if the way CCF has been designed is very interesting. So can't we just do this thing? We can take an off-the-shelf trusted protocol like MinBFT, MinZZY, anything, and then have any committee or consortium which is actually running that protocol, and we can call it this. We can say that it is providing the same services that CCF is providing, or how is it different from that?
Okay, so in terms of, I'll take the second question. Sorry, I feel like I forgot the first question. I'll take the second question first. So in terms of how this differs, so the getting the multi-party, this has been a very high level overview. Getting the multi-party consortium stuff to work is actually quite involved. I think you probably could borrow just the multi-party governance aspect and apply this to a traditional BFT protocol if you wanted to have essentially like a BFT on top of a trusted execution environment. So you can have the the safety guarantees of BFT plus TEs with the multi-party governance. So I think it is possible. I think it is possible to port it over. I think it would be quite a lot of work to do so, but I think it could potentially be quite interesting. We have also experimented with putting putting BFT protocols inside of CCF. There is an experimental fork of CCF that does that, but for now we focus predominantly on the CFT version of it, which is the version I focused on today. Can you remind me of the first question again? I'm so sorry.
No worries. So the first question was how is CCF providing the privacy? Because
Yes.
essentially the committee members or the consortium members would be knowing all the transactions, right?
So the consortium members individually do not know the transactions. The transactions are only ever kind of in the clear inside the T's on the nodes. So if separately enough consortium members got together, they got a copy of the ledger from one of the nodes, and enough of them got together that they could generate the ledger secret using this, the K of N stuff that we talked about before, then they would be able to decrypt the ledger. So if what the constitution is programmable, the default constitution is just majorities. So if a majority got together and worked, they can decrypt the ledger and they could read the confidential data inside of it, but an individual consortium member could not. And you can change the constitution. So you could require actually that all consortium members would need to provide their recovery shares in order to decrypt the ledger. It's really a trade-off between kind of how easy you want to make decrypting the ledger. Does that answer that question?
Yes, thank you.
Thanks, Yash. Shivam, do you want to ask your question?
Yeah, hi. So I have a slightly orthogonal question. So does CCF allow like arbitrary application logic to be implemented, or does the app developer need to learn about the limitations of the underlying SGX or SEVNE environment that you're using?
Yes, thank you. That is a very nice question. So CCF does allow essentially arbitrary application logic. So you can write your CCF application in either like JavaScript or TypeScript or in C++, and you can plug it then into the CCF service. You don't need to know anything about kind of SGX and AMD, SNP and all of that kind of stuff. All you really need to do is to write your application such that the state is stored in a transactional key value store. Is the whole kind of idea with CCF is to try to make writing applications as easy as possible, because we're desperately trying to get people to basically move from traditional systems to systems that have some better guarantees. And so we're trying to make it as easy as possible. There is, if you look on GitHub, there's a repository which is linked to from the CCF website, but it's a bunch of sample applications for CCF. These ones are all JavaScript and TypeScript, I believe, and they are implementing different things like a banking app like the thing I mentioned, or like a forum and things like that. So it should be pretty easy to do. And I can say from working on building stuff on top of trusted execution environments that having to learn about how to program on SGX is not fun, and we do not ask application developers to do that at all. That's very much something we're trying to abstract.
Thank you.
Itai, do you want to go?
Yeah, hi Heidi. I have a few questions, but I'll start with one. So I guess I'm wondering about why you believe crash fault tolerance is enough. And I think my mental model is that kind of you take a Byzantine party and add a TE, and perhaps that kind of limits it to some sort of omission type failure. So I guess maybe you can comment on that.
Yes, so I'm an optimist. I think that we should trust in TEs in general. I know that SGX has had many flaws. I am on a corridor of people who break SGX as their jobs and for fun. So there has been a lot of issues, and there's a lot of reasons not to trust SGX. It is the case that most of the exploits in SGX are confidentiality ones, as opposed to ones that violate integrity. And we have applied mitigations to to these problems. And now we see all different trusted execution environments. So there's the AMD offerings of SMP SEV, as well as Intel TDX. So I think Ts are improving, they're getting better. I think we will be in a position in the future where the assumption that like these things are trustworthy, and therefore essentially for safety at least, it reduces a Byzantine fault down to a crash fault is a realistic assumption to make. And I actually think that this model isn't necessarily weaker than a Byzantine fault. It's a different model. And by that, I mean, when you're thinking about Byzantine fault tolerance, we're saying, right, so for safety, we have this F, and if more than F fail, then we can no longer guarantee safety. When we're using crash fault tolerance on top of Ts in such a way, we have F still, and liveness very much still depends on F. If you lose more than F, you definitely lose your liveness. But in terms of safety, actually, if you assume the Ts aren't compromised, and so safety attacks are just attacks by the host, then you actually do still have safety, even if all of the nodes are being attacked, which is really nice and I think quite a powerful guarantee.
Thank you. So yeah, I'll go with my second one. I guess just to comment, my question more was about crash versus omission. But I guess my second question is around the integrity. So there you send you have a Merkle tree that you sign periodically. Yep. So I wonder, how does that kind of combine with the fact that you have some transactions that are secret? So if they're secret, I can't kind of understand what I'm kind of signing on, or how does that work? The secret versus public and the integrity signing, is there a challenge there?
Yeah. So to take a step back, so CCF provides these two different types of transactions. Generally, we think of like the internal transactions and governance stuff as being public, so it's nice and easy to audit, and the application transactions generally as being private, although you can totally do private ones as well. The signature transactions are therefore public transactions, which is really nice. It means anybody should be able to verify, you should be able to verify the ledger, the integrity of the ledger, without even being able to decrypt the private transactions in the ledger. So that's really useful if you're doing a disaster recovery, and so you get a copy of the ledger before you even begin going around trying to collect shares to do the decryption. You can check, like, is this even a valid ledger, or has this been tampered with, or should we just completely throw it away? In terms of having these as separate mechanisms, it's actually quite nice to have the integrity and the encryption separated, because you're allowed, the integrity is over all transactions, whereas the encryption is done on a per transaction basis. So that decoupling is actually quite useful.
Thank you.
All right. Thank you, Heidi. So with that, let's move on to our next talk. So Mick, do you want to share your screen?
Yep. Hang on one second. All right. I guess first question, are you able to first off hear me, because I'm having headset issues this morning?
Yes, we can hear you. Yes,
can you see everything okay?
Yes.
All right, good.
All right.
We'll go ahead and get started.
Yes, I think our next speaker is Mick Bowman. He's a senior principal engineer at Intel Labs, and he's going to talk about blockchains and trusted execution environments and SGX. Oh.
All right, so the origins for this talk actually go back several years. I was doing a presentation at Crypto the week that the Spectre and Meltdown attacks for SGX were announced, which did make for a rather interesting presentation at the time. And I think the good news is that a lot of our work from the very beginnings has started with the assumption that trusted execution could be attacked. And so we had some reasonable answers for that. We start with this sort of view of trusted execution as providing sort of confidentiality, integrity, and attestation. But ironically, even though I work for the company that builds trusted execution environments, I'm going to kind of take the other view of this, that we also have to deal with the reality of side channels, single vendor issues, and single roots of trust in it. So that presentation at Crypto years ago kind of reset my thinking a little bit about how to frame the problems of the relationship between trusted execution and blockchains or decentralized computing in general. And one of the things, though, is sort of going back and looking at, what do you really get from a blockchain? You get an immutable record, you get cryptographic assurance, you get trusted authority, it's community-based. These are all good things for it. But you also get a lot of negatives, the inefficiency, the redundancy, and to a certain degree, we talk about poking the balloon. Yes, we've got a really nice solid cryptographic core, but we've moved so much complexity out to the outside that we've created a lot of vectors for attack on these systems from things like key management. But really at its core, everyone sort of trusts blockchain, even though they kind of don't trust trusted execution environments. And that's kind of a problem, because when you look at the center of the blockchain, there are a bunch of assumptions about sort of behavior in sort of the proof of star consensus about the behavior of the miners, or frankly, from the traditional VFT, we still have this sort of assumption that there are only F bad actors in our 3F plus 1 or 2F plus 1 assumptions. And what happens when those assumptions don't hold? When in fact there are more bad actors, or when the miners are motivated to behave in ways that are unexpected for what we have. At the end of the day, blockchains aren't perfect. They have the same kind of problems that we have with trusted execution environments, that there are a certain set of assumptions. If those assumptions hold, then it works the way we expect it to. But those assumptions don't always hold, and we have to understand how the behavior of the systems are affected when those assumptions don't hold. So, this is the question I get asked about TEEs all the time. Why use a TEE if it isn't perfect? Why use a blockchain if it isn't perfect? Because for most of us, when we're looking at these technologies, the benefits that we get out of consensus, the benefits we get out of establishing this community-based trusted authority is worth the risk. And what I really want to argue today is that what we need to do is to stop the language of security when we're talking about blockchains or trusted execution environments, that's not helpful in designing solutions that combine the two technologies together. That what we really need to do is to use a language of risk. That the technologies we're building are not perfect solutions. We have to understand that. And what we're really doing is trying to manage risk. And we're applying technologies in a way that help us reduce the price that has to be paid for decreasing risk. All right, so with that lead in, let me just go back and start talking about some of the work that's been done. I've had a number of conversations with people about trusted execution environments, and to a certain degree, there are sort of these assumptions about TEEs being used for confidentiality. There's a whole confidential computing consortium that manages the messaging around how trusted execution provides confidentiality. And in almost every situation, the use case that's really being concerned in those situations is somebody outsourcing a workload to a CSP, wanting some form of compliance that the CSP at least will be challenged to access the information that's being outsourced and executing. So the press tends to focus on the confidentiality aspects of TEEs. And so that's really what matters to most of the trust execution environment individuals. But what we've found when we're looking at the decentralized computing, and this is one of the things Heidi was just talking about earlier, is it's really about confidentiality plus the verifiable integrity that we get for it. So the trusted execution environment not only prevents observation of memory, protecting the sensitive execution, but it also protects the integrity of that execution as well. What that means is that we can run the same set of code in theory on multiple enclaves, and we should be able to get exactly the same results out of it. We should get some level of determinism or idempotency out of the execution for it. And then the second aspect of that verifiable integrity is that we can prove to somebody else that we got the correct answer. And so in a way, what that really means is that I can ask an enclave to perform a computation, to increment a counter. And I can get the evidence that I need back from that enclave and hand that to somebody else and prove that the counter has been incremented, even though they don't have access to the hardware or any of the details of the computation that happened. It's that third-party verification of the integrity of the computation, which is really the useful property that we want to take advantage of for these decentralized computing. What it allows us to do is to take the TEE and make the TEE itself our trusted third party for our multi-party computation. So kind of going back then and just sort of positioning the TEE in terms of how decentralized compute works, you know, our basic transition of decentralized or multi-party compute has been that we take something that was originally sort of authorized and managed by a single organization, and we take that computation, we distribute it across a community, and the community is the one that rubber stamps the correctness or the integrity of the computation that's been performed. In some cases, we have, you know, the public blockchains where that community is potentially tens of thousands of individuals. And in some cases, that community for the enterprise blockchains, the smaller things like CCF, maybe a community of a few tens of participants. But it's still really decentralizing the root of trust from a single organization out to this community. What we want with the trusted execution environment is to get the same sort of risk profile, but without all of the inefficiencies that go along with the community vote. So when we're doing it in a community, if we add members to the community, we don't get better performance, we don't get better transactions. It costs us in terms of additional complexity and computational communication resources. And really all we're getting when we add all of that additional hardware is just an increase in resiliency. It's not a functional improvement, it's simply a resiliency improvement. What we want to do is to see if we get the same kind of resiliency without the kind of redundancy. If we move from the community being our trusted third party to the hardware-based TEE as a trusted third party, what can we do? And so we've done a variety of things at Intel through the years, consensus algorithms and smart contract systems. A lot of our work right now is sort of focused on a core technology that we're calling private data objects. It's a research system, it's had influence on and is basically the core of the Hyperledger Avalon project. There's some work that we did with IBM to turn this into a Fabric private chain code to extend Hyperledger Fabric for confidential compute as well. And right now, honestly, most of our research is not on the PDO platform itself, but on the kinds of applications that you can build on it. So we're doing things like confidential NFTs and decentralized identity services on top of this. But at its core, what a private data object is really a smart contract that's bound to some chunk of data. The data is encrypted. I'll talk about that in a minute, but it's always encrypted independently of the enclave. The data is wrapped in a smart contract, and that smart contract provides the policies for accessing, negotiating, and updating the data. Since that smart contract is exclusively executed inside a trusted execution environment, we can always assume the tight binding between the smart contract and the data that way, so that the only way to access the data is through the contract. It has some really nice properties that it means that policy and data become sticky no matter where they move through the network that way. It also has some really nice properties around execution that way. But at the end of the day, we still need some kind of root of trust for what the authoritative copy is of this object, of these private data objects, and we trust the blockchain for that. And so in some ways, this goes back to, you know, our kind of theme that we've had in the last couple of presentations about, you know, the blockchain makes the TEE better in this case, because we can get some notion of authority. There are a bunch of other things that we could talk about in here, and I'd be happy to talk about them offline as well for that. So the architecture for the private data objects really involves 4 separate things. There's the contract enclaves, the decentralized storage service that we have for it, the provisioning service, and then the decentralized ledger for it. So the idea behind the enclaves, the enclave service, is that this is the place where we perform, where we operate on the data, where we execute the smart contracts on the data. We've got some hash of the data that comes in and some hash of the data after the operations are performed on it. And that represents a transaction. That transaction is signed by the enclave and then submitted to the ledger for commitment that way. And so really what we're doing is all of our smarts and intelligence is going into these enclave hosting services, the contract enclaves that are there. They become, in a sense, that trusted third party for correct execution of the contracts. There are a number of supporting services that we need around it. We have a decentralized storage service, which gives us, okay, we have some notion, we've been talking about it as Byzantine resilient notification. But it's really, rather than the system managing storage, the decentralized storage is really about a well-known, well-bounded period over which the contract state that data can be copied into some user's storage. So we do not presume the long-term persistence of storage. That's something we don't believe that the central service should be responsible for in that sense. But we do provide guarantees for notification on updates so that anyone who's participating in the contract has an opportunity throughout the state of the contract when it changes. The contract provisioning service is really in some sense, and I'll talk about this a little bit later, it reflects the need that we have for being able to do key provisioning for these encrypted states outside the ledger itself. So we do a simple multi-party protocol for doing key generation and key regeneration through these provisioning services on the outside. Really what that means is that no enclave can control, no single enclave can control the provisioning of the keys. That this has to be a community-based computation for it. But since it doesn't happen very often, it's a really lightweight protocol for us. It's okay that it has a level of redundancy for it. And then finally, we have the distributed ledger. And the ledger is really about, it's really a commit log for the updates to the state. But it also serves the purpose of being our registry for the enclaves. So it is a community decision through the ledger to decide what constitutes an acceptable enclave. And so we can differentiate, for example, between enclaves, let's say in a Stanford grad lab, and enclaves that are running in the Azure Confidential Compute Services by Microsoft. We can differentiate between those in the registry that we provide. The ledger is also used for basically providing interrogatable information about all of the participants and the contracts and the history of each of the contracts and the contract objects that way. So one of our principles is that everything should be interrogated, that you should be able to view the provenance of all pieces of this and determine the risk. And the log serves that purpose. And by the way, Heidi, this is based on CCF. We've been a long time user of CCF back from the 0.14 days, I think, 3 or 4 years ago on that. Okay, so attacks happen. So one of the characteristics of the architecture I just described is that in some sense, the sole arbiter of truth about what happens in a transaction is given back to the trusted execution environment. And the obvious question should be, why would you trust the TEE as the sole arbiter of truth? And the answer to that is you shouldn't. not by itself, or at least not blindly, trust in that TEE is probably unreasonable that way. Well, okay, then the question that everyone asks me when I do these presentations is TEEs have flaws, they can be attacked. They're just another piece of security technology. What good are they really? And what you find in the community tends to be two camps. Camp number one is it works and you should use it everywhere, and it's a lovely technology and it makes everything work better and it's fantastic. And then there's camp number two, which says, well, look, we can't theoretically prove that it works in every situation, and so therefore we shouldn't use it anywhere. We should just ignore its existence and throw it out that way. Neither one of those extremes is probably helpful in understanding how the technology can be used. That there are some very reasonable middle ground assumptions. And again, this is where I'm going back to that language of risk rather than language of correctness. That when we look at the TEE, as we design systems, the principles we've found that help us understand where the TEE is appropriate and where it's not appropriate. Number one, it works unless it's explicitly broken. Number two, it's expensive to break. There are a lot of things that you have to have in line in order to be able to attack these trusted execution environments that way. And the final one is that every TEE is situated in a larger context. It is simply one piece of a security solution. It is not the solution that way. And so we ended up with these kind of design principles based on those high-level assumptions. The first design principle is, kind of as Heidi was saying, we assume it works and then we assume it doesn't. We can get tremendous performance improvements, efficiency, and confidentiality using the TEE, but we also ultimately have to figure out what we're going to have to sacrifice, performance, efficiency, or confidentiality, in order to accommodate potential compromises. How do we deal with the situation where the TEE doesn't work and it's appropriate? This is particularly important for decentralized systems because in some ways it's the worst case scenario for the threat models for TEEs, because oftentimes the participants have physical access to the machines. Second basic design principle is make sure that there's no big targets, that we should not compromise of a single TEE should not allow a scalable attack on the rest of the system. So we assume a limited budget for the attacks. We want to make sure that we compartmentalize information as much as possible across the system. And the final piece of this is a little harder for us as kind of computer scientists because it's really about the situational aspects of this. Deployment is a fundamental part of the protocol definition. It doesn't show up in the state machine necessarily, but it really matters. And my canonical example for this, and I can pick on Berkeley or Stanford, but a TEE that's running in a Stanford grad lab has a very different risk profile than one that's running in Microsoft CCS. The Stanford grad lab, those who have physical access to the machine are highly motivated to break it. It'd be really cool, and they get a great paper out of doing it. Whereas those who are running in CCS, they get sued if they make it available to operators because of the arrangements that we have with it. So we can bring a lot more to bear on that. We need to be able to differentiate when we're performing computations between those two situations. It may be that for a low priority, low value transaction, I'm perfectly fine with it running in the Stanford grad lab. But for $1 million transaction, I want another level of security in the situations for that. So as we move that back to the private data objects, this notion of assume it works, then it doesn't, PDO has this notion of an optimistic commit, that we commit on the claim of one TEE, but we allow revocation on the claim of N TEEs. So we can have some set of observers that can say, hey, look, that was committed, but it's really not correct. One of the observations about this is that although we tend to focus our consensus in sort of traditional distributed consensus on the correctness of a particular commit, in the case of TEE commits, If one of them disagrees with the rest, that means something's wrong with the TEE, assuming idempotency and determinism in the computation. So it's not just that we can claim that the transaction's bad, we can claim that the enclave is bad, and then we can take further actions based on that. So as far as the no big targets, this is where we go back to that provisioning service that we require explicit and limited provisioning of the keys so that there are no universal keys. There are no cross-ledger keys. Every enclave has at most a limited subset of the keys so that any attack that's successful is only successful on the things that have been explicitly provisioned to that enclave. And the final thing is the deployment part of it. And this is where I go back and, the nice part about having a ledger is that all the information about establishing the veracity of a computation can be interrogated through the ledger. So we end up with an enclave registry that you can see the policies for why an enclave was accepted. We have policies about contract provisioning, where it's been provisioned to execute, who participated in the computation to do the provisioning, how recently has it been rekeyed. All of those properties are things that are in the ledger and can be interrogated. So the idea is that anyone who wants to participate in and use this can interrogate the contract and the contract object for it. All right, so coming back and just kind of bringing this to a close then, we can ask the same question that we asked about the blockchain. Why is the TEE if it isn't perfect? And really at the end of the day, because of the performance and the confidentiality potential that we get and the efficiency, for some cases, it's worth the risk to do. All right, then just sort of back to that notion of decentralized computing with the language of risk and what the lessons are that we've learned. The first and foremost is be cognizant of hidden assumptions. There are always assumptions, be aware of those. It's the assumptions that people are attacking, not the core technologies in most cases. Second, any system has to be designed for the assumption of failure. I don't care whether it's a lovely Byzantine fault-tolerant protocol or a Nakamoto consensus or a TEE-based system. You have to design with the assumption that there's failure, and that really means that there has to be a defense in that. So I guess the final conclusion here is that when we're thinking about TEEs and blockchains, remember there's no perfect security technologies. All of these technologies are ones that we are applying to reduce the risk with some cost assumptions about what we're willing to tolerate. That's all. Thank you. Questions?
Thanks a lot, Nick. We open the floor for questions.
Maybe. Hi, maybe I can get started. So very interesting talk, Mick. It's a very different perspective and I really like some of your even sentence. It's the way you put it, like the risk. So do you have a nice example that you can share? You can instantiate how to look at the risk for an example. I mean, I see we are explaining the example how to look at it, but if there is an example, that will help quite a lot because it's a very systems related thinking and not like extremely like computer science thinking that you're bringing here. An example will be really helpful if you can give one.
Right. So again, sort of staying in the TEE space, let's go back to that notion of Stanford versus Microsoft for enclave hosting. So I have two enclaves that I can choose to execute a method on, right? So that I can perform some computation on one of the two TEEs. One of those TEEs is situated in, I love the guys at Stanford, so I get to pick on them all the time. It's in the Stanford Grad Lab, right? And that trusted execution environment that's running in the Stanford Grad Lab is low cost, right? Because they're just making it available as a free service. But what I have to be careful of for something that's running in that grad lab is that all the students in the grad lab have physical access to the machines. And at least in our case, most of the side channel attacks require, or at least are much easier if you have physical access to the machine, right? So I don't know what else is running on that server with it. And they're kind of motivated because it would be really nice to have a paper about how they broke some transaction on the TEE. This is why people like to go after SGX. It's really fun to break it. It's very popular to break it. So I could run that transaction. So I can run a transaction there, or I can go over to CCF or CCS, where I'm going to have to pay the overhead of hosted services on Azure. So I have two options, right? Option number one is that I can go to a free service that's running in a grad lab. Option number two is I can go to a paid service that has a managed computing environment on it. So let's say that I've got a 10-cent transaction. Do I want to take that 10-cent transaction and run it on a service where it's going to cost me $1 to run that transaction? Or do I want to run it on the free service? Well, the risk is higher on Stanford, but it's a low value transaction. If it gets broken, so what, right? But now contrast that to, I have $1 million transaction, or I'm going to perform some NFT ownership transfer for a $1 million piece of art. I would much rather go someplace where I have a higher trust or a higher assurance that it's going to be performed correctly than I would to the grad lab for it. And so my risk profile for each of those is going to be a little bit different. And what I need to do, I mean, what our focus has been on is exposing those properties so that individuals can make those decisions as to where they want to perform the computation, based not just on cost, but on cost and risk. Does that help?
Yeah, that helped. Thanks. Yeah.
Thanks, Mick. Suyash, do you want to ask a question?
Yes, thank you for the presentation. I think I really like the part where you said we can do actually contract execution inside the TE. One thing which I was wondering is, what is the implication or cost of doing that? Because generally, if you have a host machine with a lot of cores, you can use the contract and you can exploit those cores. You have a lot of access to a lot of memory. But now inside the TE, I'm assuming the memory, the cache, and the hardware is limited. And if you need to run a code and you might need more memory, you might have to do paging, you need to do syscalls. Isn't that quite expensive to do if in comparison to just running it on the host machine? So how are we getting the performance there?
So there are a couple of parts to answer to that. So kind of worst case is that I have to run it on the Ledger node. If my application requires me to run all of my execution on the Ledger node, then I've got a problem for scalability, right? When I run out of compute on the Ledger node, I'm a problem. So let's just hold that one off to the side. A lot of our work has been focused on how do we move things off the Ledger so that we can do the computations in a trusted execution environment where it makes the most sense. Now, the Sapphire Rapids servers that are coming out and the Ice Lake servers that come out do not have the kind of memory limitations that earlier versions of SGX had. And we're routinely running very large computations. So a lot of our application work right now is looking at how to do contract-based training for machine learning models. And so the data, we preserve the confidentiality and the value of the data as part of the training processes. And those operations are using a substantial amount of memory and compute. And it's precisely because we've moved it out of the Ledger that we're able to actually do those pretty substantial computes.
Yeah, that makes sense. Thank you.
All right. So in the interest of time, so there are a couple more questions on the Q&A, but in the interest of time, I think let's stop here. Mick,
I'll answer those on
the chat.
All right. Thank you.
Thank you so much, Mick. So this ends the first session of our event today. So we'll break for 15 minutes now, and then we'll reconvene for the next session, where we'll first have a panel with all of the speakers, and we can have more discussions and more questions, and then we'll have 2 more talks. So I'll see you guys in 15 minutes. All right. It's noon. Welcome back, everyone. So we'll start our next session now, and the first part of the session is going to be a panel where, let's engage in interesting discussions and try to have our questions answered and learn from others. So we have our speakers as panelists. So you heard already from some of them, Mick and Heidi. You already heard from them. Natasha could not make it due to a scheduling conflict, but we also have Matt Green and Nick Hines and Jonathan. So there are speakers as well, but you haven't heard from them as yet. So welcome all of you. So to organize ourselves, we can have direct questions from the audience, but we also have assembled some questions ahead of time, and all of you feel free to add more questions, vote on existing questions at this link that I have shared. So given we have a short amount of time, let's get started. So among all the questions that have already been posted, there are two that have received a lot of votes, and there seems to be a high amount of interest on answering these questions. So the first one says, T's can be thought of as converting Byzantine faults into omission faults. And if that is true, what are the challenges remain besides developing good omission fault tolerant protocols?
I'm happy to start with that. So a big challenge is liveness. In particular, the untrusted host is still responsible for instance, sending network messages. And so you've got all your normal liveness problems, like you might genuinely just have network partitions. There might be asymmetric partitions, there might be delays in the network, but then you've also got this host who could potentially be malicious and could deliberately be trying to drop packets, or perhaps ensure reorder packets between different clients. So perhaps they want one client to have priority over the other. So I think liveness is still very much an issue. It's an issue in classical systems, but it's an issue when we're building on TEs as well.
I kind of want to just say that I don't agree with this notion that we can just trust TEs to work in the first place. I guess I'm a little skeptical. I think that they definitely provide this sort of theorem that we can convert one type of fault into another type of fault does depend on the fact that globally every single TE is working perfectly, but that's obviously not true. And at the end of the day, they're not going to. So the question is, kind of how scalable are the breaks on TEs? How much of the network can we damage, as an attacker? And what does that mean? And so, I mean, this is not really a huge observation, but it makes me nervous seeing people say things that are quite that absolute.
Does anyone want to add to this? I think interesting thoughts by Heidi and Matt.
I can follow up from what Matthew said a little bit about that. So this is something we think about quite a bit in the context of CCF. And as I said in my talk, for that talk, we very much assumed that these were just like trustworthy things that definitely did what you expected them to do. One thing I think that is very interesting is this question of like, if TEs are compromised, how do we detect this? How do we prove it? How do we hold individual nodes and therefore their operators accountable for that? And how do we basically reduce the blast radius so that a compromised TE may be able to take some actions, but aren't going to be able to completely invalidate every guarantee that you have about the network. Particularly in the context of CCF, actually, there was an NSDI paper last year, which was about IACCF, which was a proposal for individual accountability in permission blockchains after TE compromise. I can drop a link to it in the chat.
Go ahead, Mick.
Sorry, now I got too many buttons. There's been a variety of things. I mean, building off of what Heidi said, there's been a variety of things about sort of honeypot kinds of approaches to doing identification of TEE errors. And it kind of goes back to that point I was making about if you assign some level of determinism or idempotency in the computations, then when you get a failure of a computation, when a set of TEEs doesn't agree about the output, then you know that one of the TEEs is bad or has been compromised at some level. So the other observation about this is that failure is more than failure about an individual transaction. It's about a failure of a node. And sometimes you can retroactively identify what the cause of that failure was.
So I guess there are kind of two aspects to this. I'm not thinking from the point of view of consensus because that's not really the area I work in, but it's all computer security, right? So the two things that scare me, we really have two different concerns. One is somebody behaves maliciously in an identifiable way, and then we have ways that we can deal with that. We can identify the bad behavior, and we could do the usual types of things that we do to unstake people. The question is if you have some economic, there's some economic incentive not to misbehave. Is it okay that you're the one being punished because somebody hacked you? Maybe that's not necessarily the solution, but that's life. We have to figure that out. But the things that scare me are the problems that come up when we have this kind of privacy issue, right? So we have a bunch of secret keys that are being protected by TEEs. We can absolutely deal with malicious detectable behavior, but the loss of secrets can be undetectable. And, 50 people are sharing a key, and then that key is either secret or not secret, and then suddenly it's not secret, and then after that the entire network collapses. And so I think there's a lot of kind of fragility in these networks that people don't think about very carefully, that is some combination of key management and so on, and it makes me nervous that I don't know that the analyses are sophisticated enough to think about how these things feed back into each other.
So just to extend something that Matt was saying on that, when we look at this, we look at three different kinds of attacks. One is the attack on confidentiality, where secrets release. Very hard to detect, but correctness and integrity tend to not be compromised on those attacks. The second is when the TEE when a given computation can impersonate a known TEE. So, for example, that's when the keys inside the TEE have been compromised that way. And the third attack is where a TEE can be impersonated that does not actually exist. So you're able to create a new identity. So when you look at the possible failures, those three attacks tend to be a good characterization for the kinds of compromises that you can see.
But they're all related, right? So when Daniel Genkin and Daniel Gruss and company, Gruss go out and they steal your attestation keys, right? That's a confidentiality attack, but that immediately turns into the complete collapse of the system because now they're attesting as being a million nodes and doing all kinds of bad things in a consensus network. So anyway, I just think there's a lot of relationship between those things.
I think just to add to that, there's a pragmatic concern as well, which is identifying the attacks, as you've been mentioning. And if you look at the work, the SGX.fail paper that came out in August last year, which also highlights the gap between identifying the attacks, providing the mitigation, and applying the mitigation. And I think when you start talking about deploying TEs in production and potentially securing blockchain and financial values with these TEs, that's extremely important to take into account.
Thanks, everyone. So I think I'll move on to the next question, which in some ways is the other side of things, where one way of viewing TEs is that it is an ideal assumption. It is you can think of it as a trusted third party in some ways. Right. So from a technical standpoint, I think part of this, I guess, was answered in the previous question, but I think I'll still ask this because there's so much interest on this question. So from a technical standpoint, does this trivialize the problem that you're working on? Because you have this big assumption.
No.
Do you want to go, Heidi, please?
I think no is the short answer. Even in CCF, when we're looking at it from the lens of trusting the TEs, is still an incredibly large amount of work. And I touched on two of the points there. One being about kind of durability of state and rollback attacks. Another one being about kind of multi-party control and kind of how you actually go about kind of checking attestation and deciding who's in the system, dealing with crash faults and things. So it doesn't trivialize the problem at all. TEs are not this kind of black magic that will come along and make all your computing problems go away, which is probably good. Otherwise, we'll be out of a job.
Yeah, same here. Actually, we are. I'll talk a bit about that in my presentation, but we actually are using TEs as a way to diminish the trust in third parties. It's clearly on the path of like removing these trusted third parties. So definitely not a one-to-one replacement in our case.
Yeah, I'm a skeptic of TEEs. Like I have already said this, right? I'm always just assuming the attacker will get better, and the attacker has gotten better. So in some sense, they work a little bit better than the traditional security measures, and that's great, but they don't work that well. But maybe they will someday, right? But the thing is exactly what Heidi said, which is that once you just make the assumption, you add the constraint that the computer, the box is secure, things don't get better, because in the real world, right, we have many boxes and the boxes talk to each other, and that talking is where everything gets screwy. And so I think it's really interesting and surprising that so few people have delved into that. Like, even if you start with the assumption the box is secure, right? Like in cryptography, we have obfuscation and we can assume all these ideal objects. And then it turns out that even given obfuscation, like we run into all these impossibility results where like you can't do things. And, doing the same thing with TEs really, I think, needs more of people looking deeply at what actually happens then. And there has been some work there, and I'm going to talk about some of that too. It just creates a new problem setting for everybody.
All right, so this is where I get to take the other side of this discussion for a minute. Yes, it isn't perfect. We're exactly right. It's like any other component in a security system. It's subject to attacks. The question is, does it make it harder? And I think that's really what it comes down to, is the cost benefit ratio for using this as part of a bigger system, not as the system, right? And so the question has this implication that if you throw something in a TEE, you magically don't have to do any other work on securing your system, and that's absolutely flat out wrong. That everything we do has to be situated inside a larger system context. In that context, the TEE can be a very useful tool for making it much harder to attack a system. And I think that's really the right view of this. It's just another piece of technology that raises the cost of and raises the bar for attackers to get it. Doesn't solve it, but it makes it harder.
But what if it makes it easier?
Then we got a problem. Either that's because because we screwed up the system design. And I would argue the same thing is true of any multi-party computation, right? Every one of these has assumptions that can be attacked. That way. There are no perfect technologies for it. So it's easy, and I would say, Matt, that it's easy to design. If you start with the assumption that it works perfectly, it's easy to design a system that is very, very fragile. But if you start with the assumption that this is just another technology, then we know how to build defense in depth. We know how to build resilient systems from end to end, and it's just another piece of that system.
What scares, I don't want to hog this conversation, but what scares me is I do see people saying, hey, we've got these tools, and then they build consensus out of it, right? So Secret Network, for example, I think it was the same exact SGX fail, right? They had a consensus seed, and what that meant was you get one attestation key and you kill the entire consensus network. And so, I mean, you can build systems using these things by assuming they're perfect that are just ridiculously fragile. And I think that you're absolutely right. Obviously, we shouldn't do that. But yet people did do that. So how do we analyze these systems to make sure we didn't?
Not disagreeing, but how many of these technologies that we've had through the years are also in that same boat? right? That we throw too much trust into it, and I would say the same thing about our blockchain networks, that our consensus protocols are things that we trust, even though they have been shown to be faulty.
So just as an aside, we have a talk from Secret Network tomorrow. So we'll make for an interesting panel discussion tomorrow, I guess, because Guy is not here today. But along these lines, right, I think we're talking about killing or attacking SGX and ways of breaking a TE. So I think one of the questions is, can you actually guess the dollar cost of breaking a TE? So Mick, in your talk, you did mention, it's very expensive, and there's an explicit question asking, hey, how expensive is it?
So we've actually spent a fair amount of time to the last almost decade now of looking at this for what the cost is for SGX, and effectively it's not possible. I mean, you can always sort of make approximations that what would be the cost of a particular form of attack, but since you don't know the broad spectrum of approaches that somebody might take on it, and to be honest, SGX is going to be different than SEV, is going to be different than Keystone, is going to be different than Trusso, for the approaches and the situations and the assumptions that are made. Depends on your memory architecture, it depends on your bus architecture. It's going to depend on all of these things and what the rest of the assumptions are that you're making for it. So there is no one formula. It really just has to be thought through for each individual situation and case.
So, but I think just to extend that question, if you were to put a number to it in terms of dollars, and you pick your favorite case, or pick two extremes, and I think if you were to put in a number to it, is that something that we can potentially do?
I don't think putting a number into it is the right thing to do. I think putting a situation or context, yeah, Matt's laughing at me because I'm dancing around the question. But putting a number to it, I don't think is the right thing to do. I think the question is, what's the context and what are the things that you need? What are the assumptions you're making? Right? If you're assuming that physical access to the machine is limited, then the answer to the question is completely different than if you have physical access to the machine. If you're talking about an MPK version of it, it's going to be different than sort of the original style of SGX memory controllers that are going to be different. So I really don't think you can put a dollar amount to it. What I would say is just, I think a more interesting form of the question is, what do we know about attacks in the wild? We know a lot about the theoretical attacks. What do we know about the attacks in the wild? Until we start to see those more frequently, it's going to be hard to figure out exactly what's happening. And this is why I go back to some of these honeypot things, about making confidential information available just to see if somebody will break it, kind of things, just to create those targets for it. I don't know the answer to your question.
It is worrying that the first application we found for this is securing like billions of dollars. So like if there's any way you're going to accelerate the development of those attacks in the wild, I guess we found the way. So, I mean, good for us. We'll see what happens.
Others, do you have any thoughts on the question? All right. So if not, so I think I'll ask one last question, and then I'll open the floor to the audience to ask. So I think this question seems interesting because it's related to two of the talks that we saw earlier today. So I think the question says, Natasha says, we cannot have a performant BFT protocol with trusted hardware and 2F+1 parties. And actually Heidi claims otherwise because CCF requires 2F+1 parties and uses trusted hardware. So I think what is it that we are missing in the process?
So since Natasha's not here, I'll take that. We in the thing I presented today, this is very much trusting T's. So that is very much at the core of why we are able to do this 2f+1, and we're essentially redefining a Byzantine attack to say a Byzantine attack is the non-TE side of a host acting maliciously, as opposed to the TE side of a host. So it's a difference in definition. I would say, we have very different approaches to handling rollback attacks as well. So as I explained in the talk, we do end up in a situation where you can completely lose liveness if you were to say lose all your machines at once, because we don't have a different solution for the rollback attacks, and so you end up in a disaster recovery protocol position. For us, we think that's actually really good because it allows us to basically optimize for performance. We avoid having to use distributed monotonic counters. There's a bunch of interesting strengths there, but there is this situation where you can end up needing to do a disaster recovery. So we've made compromises in different areas. I think for CCF these are the right compromises, but they're not necessarily the right compromises for every kind of consensus system on top of TEs.
Okay, so I think with that we still have 10 minutes, so I'll open the floor to everyone to ask questions. So if you have a question, please raise your hand and we can allow you to talk. Aniket, please go ahead.
Yeah, so I'll get this started very quickly. So we did talk about the discussion on compromises, right? So what could be nice to learn is that we have some understanding for the compromise in the non-TE world, and correspondingly we try to provide systems. And let's say we look at the compromises in the TE world. Are there some conceptual fundamental difference that we can represent and say that that's the reason when we build system based on TE, these are the things we should take care of. While we build system with non-TE world, we do things differently, and that could be looked at differently. One example could be when we talk about in non-TE world, we say that we go for N programming or have multiple softwares available, use different operating systems and hardware, so that the attacks does not reflect from one system to another. But in TE world, that could be hard or stuff like that. But yeah, my question is indeed, are there patterns to understand, and what can we learn from them?
I feel like this is a Mick question more. He's the one who's been building TEs, but.
Thanks for volunteering me, Matt. Are there design patterns for this? I think yes, there are some design patterns that are things that we could look at as reproducible, and some of that stuff I was talking about that don't make big targets because it's hard to identify when some of those targets have been compromised. If you really believe in it's costly or hard to compromise a TEE, then make sure you don't have scalable attacks. That compromising one does not allow you to compromise the system as a whole. Right? You should not have single keys anywhere. There has to be something that's decentralized and compartmentalize information on it. So I guess I would go more down that path of it's not rocket science. I mean, we've been doing a lot of these things for years. It's understanding what the vectors are for the attacks as best you can, but assume that, and this is why I was kind of talking about the different modes of attack before. I don't know how we get into those three situations. Right, it could be side channels, it could be some other form of compromise, right? I don't know how we get into those three situations, but if I can start understanding what the implication is for each of those three different kinds of attacks, then I can start designing my system appropriately. So, and by the way, if there are more than the three, if you can come up with more than three, please let me know. But those are the three that when we do an analysis of the security of the system and the risk of a system, we look at those three vectors, right? Compromising confidentiality, impersonating an existing TEE, and creating new identities that are not based on the root of trust for the system. If we think about those three attacks, that gives us a holistic view of how things might pan out in the future.
building on that, when I look at papers in this space, they tend to have one section that says like threat model, and they say we assume these things, and given these things, we provide these guarantees, and that's nice. I really like that they're upfront about kind of the threat model that they have, but it's very much a one-shot thing. These are the assumptions, these are the guarantees. And what I would love to see, particularly in the academic literature, is this kind of scaled model where you say, you know, assuming everyone, you know, does what they say they'll do, and all our assumptions hold, these are the wonderful guarantees that we provide. Assuming next level that like there are, you know, some crash faults or some liveness issues, some delays in the network, right? Here's what we provide. Then moving on to like TE compromise and things like that. And here's, you know, can we at least provide like a bit of accountability? Can we reduce the blast radius of attack and stuff? Because it's very much this kind of staged model where you have different sets of guarantees depending on the assumptions that you're making, but for a single algorithm. That's something I'd really like to see more of in this space.
Yeah, I think it's really hard to figure out. Like the problem is that when you design TEs, you end up with this kind of you know, a very homogeneous system, right? You're gonna have thousands or millions of nodes that all use exactly the same software and exactly the same hardware. So then you say, you know, like, oh, it's totally secure, but of course, in practice, you know, that one vulnerability. And by the way, we see this a lot outside of the networking space. Like if you look at mobile devices, for example, we spent a bunch of time, my grad students and I, looking at like, how are people breaking into pins on mobile phones? And the answer there, it's not always a TE, although it is on TrustZone on Android phones. It might be a piece of hardware, but it's an exploit development thing. And then it becomes incredibly scalable as long as you do it for millions of phones and you keep everything very secret. And the challenge there is, what do you do about that? And you know, it's really hard to come up with a homogeneous set of TEs. Like it completely militates against running lots and lots of different software and hardware. So the best you can really hope to do is like constantly be looking for these vulnerabilities, trying to characterize them, and then hoping that you can do software updates to stop the badness. But that means having a system that's very, very software updatable. And, you know, sometimes even that's hard, right? Like we've seen vulnerabilities, not so much of TEs, but of bootloaders that are, you know, ROM-based bootloaders and can't be updated and you're just dead. So, I mean, like lots of capability to deal with these things is what you need, I guess.
That does bring up an interesting problem with one of the approaches we've used in order to fight against scalable attacks has been heterogeneity. And the distinctions in functionality across the current TEE spectrum makes that really hard. I mean, we've gone back and tried to look at what would it take to get the same kind of functionality out of our contract execution engine on Keystone in particular. And it's hard. I mean, at least we have the advantage we're using WASM, so we have, you know, sort of architecture independent execution, but still trying to get the attestations to line up and what it means to have deployment, because the semantics are so radically different between the two. It's a TEE, but it's not the same piece of hardware.
Is there any initiative on the, like, for example, at the Confidential Computing Consortium around aligning, you know, attestations at least, or other kind of like common elements that you find across TEs that would make your life easier?
So there is some work in CCC about aligning attestation formats, but the semantics of those attestations is very different, right? The threat model for SEV is not the same as the threat model for SGX, is not the same as the one for Keystone. And so you can attest to the validity of a piece of hardware, but okay, this is where I get to push it back on the academic community. You guys haven't given us a framework in which we can reason about the capabilities or the properties of a TEE independent of that's an AMD SEV machine and that's an Intel SGX machine. You know, we tend to reason at the level of the hardware name, not at the properties of the security of the TEE underlying it.
So to add to that, CCF is built on SGX, but was very much designed with the idea that we might be able to support multiple TE platforms. And we're actually actively working on SEV support for CCF. It is quite the engineering overhead to try to add this and then try to support both of them. I think now that we're moving from Enclave, we seem as a community to be moving from Enclave-based TEs to VM-based TEs. I think it might be easier in the future. So I think, for instance, SEV to TDX might be less work than SGX to SEV. But that's just a theory. I'm not certain on that. But I really am looking forward to us having more diversity in TE platforms and to be able to ultimately deploy these systems across different TE platforms and also across different cloud providers. So you might have Amazon running some nodes, Microsoft running some nodes, you're running some nodes on-prem, maybe one of the other parties involved in the system is also running it on-prem, and there's some diversity of platform to really increase the diversity and kind of make these assumptions we make about faults a bit more realistic.
All right. Thank you for an interesting discussion. So I think a one line and a very simple summary, I think in my head is, TEs do help us in providing better security guarantees, but it is not a silver bullet. So there are still many challenges to solve to ensure that we have a secure and a performant system. And so with that, thank you all the panelists, and we'll move on to the next talk. So Matt, can you please share your screen?
Yeah, no problem. 1 second. Let's see if I can make it work. Hang on a sec.
I hope you can.
Let's see. Yes. Okay. Hypothetically, you're seeing my keynote. Is that working for y'all?
Yes.
Good. Okay, great.
All right. So we have Matt Green. He's an associate professor at Johns Hopkins, and he'll talk about ask not what TEs can do for ledgers, but what ledgers can do for TEs. So this is the second time we're hearing this phrase today.
Oh, no. Okay. All right. Well,
first time was not in the title.
Okay, maybe this is already kind of redundant because, I know this is a subject other people have been talking about. This is something that I'll skip this, that I have been thinking about for a long time. And obviously I work in applied cryptography. And so TEs are kind of the dream of an applied cryptographer, right? Like we have this beautiful trusted box that can do all the hard stuff and key management and also any kind of arbitrary functionality. And that solves kind of all of our problems. So the question is, in this world, is everything done? Like, have we solved all our hard problems? And I have a lot of feelings about that. I actually have a lot of feelings in general. So I figured I'd just devote the first 4 minutes of this talk to ranting about, my feelings about TEs in general in the research community. And kind of what I want to say about the research world is that there has been this kind of phase of, hey, there are TEs now, let's do everything using them. And this was an awful thing that I guess we had to flush out of our system. And I was going to call out specific papers, but then I thought that would be mean. So instead of calling out specific papers, I went to ChatGPT and had it write me a paper abstract, and then I put it into Overleaf. And this is kind of like the typical paper that you saw in like CCS or Usenix in like 2016 and 17 around the early phases of SGX, which is like, hey, look, we figured out how to like replace encryption with SGX. And it's like, great, that's incredibly foolish. And like, fine, great, we have a trusted computer, let's use it. And I'm glad we kind of flushed that out of our system. But a lot of these systems were really bad. And I don't mean bad in terms of like the researchers bad. I mean, they were dangerous, right? They didn't care at all about fragility. They would do things like the one paper I will pick on because I've talked about it with Dan Bonnet is there was a paper called Iron, which planned to do basically functional encryption using TEEs. And so instead of using cryptography, they would just like put a secret key in a TEE on your device. But that secret key was very powerful and could do all sorts of terrible things. So it just seemed like a bad idea. So I've seen a lot of things like that happen. Okay, good. Skipping that. Where I think TEs are useful is they are a great, as Mick said, they're a great layer on top of existing security measures. We can harden things rather than making them less hard. And TEs, by the way, I'm including everything from like actual full-scale TEs to like limited coprocessors like the SEP that's inside of phones. I'm not being very picky about this. And sometimes the real use of TEs has nothing to do with hacking and has nothing to do with criminals. And in the privacy sense, has everything to do with, I make you trust me? Like, I'm a slightly adversarial person, like a company. Can I just convince you that I'm not going to use your data to do data mining? And like, that is a huge application, or I'm not going to hand your keys to the FBI. Okay, last, I'm almost done with my feelings on TEs. As I was saying to Mick, what I've seen is a lot of people using TEs to build very fragile systems, and that makes me nervous. When you trust the TE too much, and particularly your TE that hangs on confidentiality of some secret keys, that creates systems where like a confidentiality break leads to an integrity break, which leads to the entire network collapsing, and it makes me very nervous. And the example is, of course, Secret Network and its consensus seed, which they apparently have fixed. I don't really know what the solution is, but also a lot of the smart contract networks do stuff like, if you're not very careful, you can end up sharing confidential smart contract data with a bunch of people you don't trust, and then badness happens. The other place I want to call out is that Signal has this thing called Secure Value Recovery, or SVR, which is just a tech preview, but basically it is an SGX-based data store. You can store people's secret keys in there. It's a really nice idea. However, deep buried in that tech preview, they have this replication idea. So they're worried that nodes will go down, and nodes will go down. So how do you deal with that? Well, they use attestation to allow you to join new nodes onto the network. And what that means is, probably there's some other access control as well, but an attestation key, a single attestation key stolen, means the entire system is toast. So you're not hardening, you're making the system much, much more fragile. It makes me super nervous. I know these folks, there are lots of other people on their team, but they've done a pretty good job of showing us how fragile these systems are. Just one last anecdote I want to add is that Daniel Genkin calls me from time to time and says something like, what do you think about attacking this system? And I say, well, why don't you attack this system? And the answer he always gives me is, I'm an academic and I can't get on that server without breaking the law. And so like he tends to attack blockchain systems because anyone can run a node for some money. But sometimes you can't even do that because maybe the validator, staking cost is $80,000. So a lot of the time, what you see as secure systems are not really secure systems. They're just systems that, these people or other people they work with can't afford to break. And that seems like a bad way to judge the security of a system. All right, good. But none of that has to do with what I want to talk about today. And I've got 30 minutes, so this is going to end up feeling a little rushed, but I want to talk a little bit about what I think were the interesting problems. Okay, so, clearly a lot of people were moving into the subject of blockchains and ledgers. People have talked about how to use TEEs to make these systems more functional. And we've seen a lot of things like building oracles from TEEs, doing consensus, doing smart contracts, doing secret and custody for smart contracts. We have seen a lot of these applications, and I think they're all wonderful. These are basically using one to fix the other. I want to flip this around, and other people have talked about this. I want to talk about how blockchains and ledgers are actually kind of a first-class cryptographic object that we should be using, not just to secure TEEs, but to secure the future world that hopefully is coming, where we actually have cryptographic obfuscation and very powerful tools, and we can use those to make secure systems in the future. And so how do these blockchains actually, let us do those things? So we think about TEs at the highest level, they're, kind of a black box, right? There is an abstract system. They've got this beautiful piece of software running inside of them, which hopefully doesn't have any flaws. They have an input-output API that's very restricted. And as a general rule, just forcing people to build restricted systems tends to make more secure software. So that's really nice. We can assume without loss of generality that they correctly execute their program on some input and they produce some valid output according to their software, which, somehow we can trust that. That comes down to a lot of cryptographic assumptions. And we'll further assume that they never leak their internal secrets except through IO that, is valid input-output calls. Did you have a question? Sorry,
Yes.
I can't.
So if you're moving your slides, then we're not seeing it. We're just seeing.
Oh, no. Okay, hang on a second. Let me, I am definitely moving my slides, and they're beautiful slides. So I don't want you not to see them. Give me a second. Hang on. I will try to share my whole desktop. Maybe that'll work better. Can you see my desktop now?
We can, I can see TEs and abstract view.
Okay, good. I will show you the slides that you missed. Did you miss all the slides? Yikes.
Yes, we
Oh.
thought you were looking at the title slide and speaking.
Oh, no, I'm sorry. Okay, well, tell me if you see it. This is my silly, I'm just going to flip through them. Beautiful pictures. I'm so sad that you didn't get to see all these things. Mostly you can hear what I said. But yeah, anyway, here's where we actually were, and hopefully it'll keep moving as we go. Let me know if it starts freezing for long periods of time. Okay, so this is the abstract view. We have these boxes that do stuff, and they do it perfectly. So, like, okay, the question was, if all problems, the question that came up during the panel was, do TEs solve everything? And that was actually one of the big things that was scary, right? Imagine a world where TEs really exist and we make them perfect. What's left? Are we just out of a job? And so, starting a few years ago, I started looking at this question with my grad students. And really the two things that you run into, which everybody here has already talked about, that TEs can't do for the most part, is they have these two weaknesses. One of them is that since they, generally speaking, live inside of a host machine, they can't talk to the world. They don't have an unfettered, uncensorable channel to the outside world. And they're dependent on the host to give them access to the network, but even to give them access to peripherals. So in a iOS and an iPhone, for example, the secure hardware chip has direct access to the fingerprint reader on old phones because nobody trusted the hardware OS to actually move that data back and forth. They didn't want people to be able to read your fingerprint. Now that's actually been changed. The secure hardware is mediated by the untrusted host when it sees your Face ID so in other words, untrusted software has access to your face in a way that it did not have access to your fingerprint. So that's actually a reduction in security. So we're going to make the assumption that the host here is malicious and they can at least censor and replay inputs and outputs. And then the second thing, which we've all talked about so far, is state keeping and rollbacks, right? You cannot really trust state necessarily unless hardware does some extra things to protect your state. So focusing in on the communication problem, right? So we're fundamentally, a TE is always dependent on its host. There are these exceptions, but at the end of the day, it's not something you can generally win just by making a few hardware optimizations, right? The network is always going to be on the other side of some connection. Cryptography can help. We can establish secure channels directly from a TEE to the outside world. But this means that we're trusting the person on the end of that channel. And so we don't have perfect access to everything. Moreover, it can always be censored anyway. And so we have to figure out, like, is the network down or is somebody blocking our connection? So a picture of what that looks like, and hopefully you can see this. A picture of what that looks like is you have this notion of an enclave sitting inside of a host talking to the internet, and the host basically has total control. And we assume, obviously, that the host, in the worst case, is completely compromised, is going to do evil, terrible things, but the enclave is safe. And, we can use a trusted party as some kind of relay and establish a secure channel to that trusted party, but then the trusted parties themselves can be compromised. The second thing that we have to worry about here is state keeping. And of course, state is a critical challenge with any TEE. And in unfortunately, many TEE implementations, the way we handle state keeping and storage is we rely entirely on the host machine. And then we use encryption under a key that the TEE knows, and that gives us confidentiality for the data, and it gives us authenticity, which is almost everything we want. But of course, if we don't have some way to make sure the data is fresh, we end up with the ability for the malicious host to roll back state and give us something that is old and ugly. And so the classical example of this, which is a real example that turns up in things like iPhones, is you have someone who has, let's say I've secured some data in the enclave using a PIN, and the PIN is low entropy. So I want to limit your guesses to 10 incorrect guesses before I lock the system or erase that data. And this is exactly what iPhones and iCloud, for example, do. And the problem here is that who's going to store that encrypted counter? So the counter gets encrypted and sent to the host. Of course, the host can just replay old counters. You can always be on guess 9 for 1 million guesses, and you'll never, ever be able to limit. And that fundamentally breaks this kind of system, but it also fundamentally breaks a lot of other systems that are cryptographic that are vulnerable to rollback attacks and so on. So this is not a good thing. How do we prevent it? Well, Mick will probably say a lot more things about this, or has already said things about this. The early versions of consumer SGX decided to implement monotonic hardware counters using non-volatile RAM. And that was awesome, except for the problem is then on the enterprise hardware, they removed all those monotonic counters. And there was actually a good reason for this. The reason was that if you're using shared hardware and some remote user, let's say you're Amazon, and some Amazon customer grabs a counter, you can't really pry it away from them. And if you pry it away from them, then the system's kind of insecure. And now they own it forever. So how do you manage that resource? And also, one of the fun things in early SGX was that there was this, they're non-volatile RAM. They're made of flash. So they die if you update them enough times. So they actually had to be throttled and controlled to keep people from just destroying the hardware. So this was a whole bunch of concerns, which they solved by just eliminating the entire problem and outsourcing state keeping to some other system that isn't part of SGX. And if I'm wrong, Mick can chime in, but I think that's the current state of the way things work. So there is no state keeping in at least enterprise SGX. So what do we do about that? How do we deal with state? People have talked about that. The obvious answer is you make a machine that has no other purpose but to keep state, or maybe it's a whole bunch of machines. And of course, if you've got SGX, you set up all those machines to use SGX or some TEE, and now you've got, some kind of consensus network of TEE systems, which is exactly, what multiple people have done. I think the first time this was published, at least, was with Rote, but obviously, data centers have been doing state keeping type things for many years back in the past. Okay, so we have some ways of dealing with this, but they usually rely on us building something novel that is not already present out in the world. And this gets worse when state is distributed. So if you're doing smart contracts, as many people here already know, you now have the problem that like the state across 50 different enclaves of a given smart contract might get out of sync. Or maybe it's not a smart contract. Maybe it's signal SVR, where we have to make sure that there is a password guessing attempt counter, and that we don't have 50 times 10 attempts to log in and guess a password. We have to make sure that even across 50 different enclaves, they all keep track of how many guesses I've made so that we have only 10 guesses. So now we have another state synchronization problem that is distributed. And so state synchronization, again, seems to imply consensus. And then maybe we have to build a consensus system specifically for this problem. And it's annoying. I just want to make a kind of a side note here that what I care about is obviously, long-term cryptographic problems sometimes. And, the ideal TEE doesn't exist, and it's not made out of hardware and software. It's made out of cryptography. And we're making like amazing progress towards having obfuscation that theoretically might work. So cryptographic obfuscation, obviously in the general black box case, the virtual black box doesn't work, but we do have some limited types of obfuscation and even tools like witness encryption plus garbled circuits that kind of get us a little bit close. And this is cool because now we actually might, maybe in 10, 15 years, if we're extremely lucky, be able to get rid of all this hardware and build things. But the problem is that these systems are even worse than TEs in the sense that software can never provide state. Like you can always rewind software, and there's just no possibility of fixing that. So this state keeping problem becomes even stronger in that setting. Okay. The idea here, what I really want to talk about is how to use extant public ledgers to solve state problems. And, we to solve both of these problems, really. Both our state keeping problem, which is something that we can do using a normal ledger, and also the problem of verifiable publication and input. So the idea here is that we have blockchains. This is not something that I would choose to use if we had to build this from scratch, but in the real world, we have, for some reason, people have spent billions and billions of dollars building these public networks, these blockchains. And so the question is, besides moving money and like doing DeFi scams, what can we do with these things that actually benefits the world? And what can we do with these technologies that's more powerful? And what I really want to focus on is thinking of these blockchains or ledgers really not as, not as something that just stores transactions, but as having an additional capability, which is this notion that we call proof of publication. And the idea here is that you have a blockchain, a decentralized network where I can post something on a blockchain and I can get back, with a little bit of reading, I can get back something that is authenticated and contains whatever I posted. And so you can think about how this might be built in two concrete examples. So for example, in Bitcoin, which is a proof of work blockchain, it's pretty easy to take a chunk of the Bitcoin blockchain. It doesn't have to be the whole thing. It can just be a fragment of the blockchain and provide that to somebody. And what they can do is if they have some past block that they know was really part of the Bitcoin blockchain, they can basically, you know, if you give them the right number of hashes, they can work their way through from that past block to this fragment, which might be, let's say, 50 blocks that you've given them. And then they can check the proof of work correctness for each block in that 50 block segment. And what they get at the end of that is not a guarantee that this was a real blockchain fragment. You could have made this on your own using a bunch of GPUs. What they get, though, is an economic guarantee that the cost of forging this could be very high. And without a lot of work, you can really increase that. And there are a lot of people who've done this. There are these Merkle mountain ranges and lots of different ways to do this. Most of them have been developed in the context of things like SPV proofs or like cross-blockchain Merkle proofs and so on. But here we can use that same technology to prove things to individual TEEs and prove that we've published a transaction. In proof of stake ledgers, obviously, it's easy to prove publication in one sense, right? Because the data is signed by some quorum, and we can show, you know, whatever the transaction, the consensus rules were that got me from like a block that I know to this future chunk of blockchain. I can show that everything seems legitimate. There are signatures on every intermediate block, including the final block where I publish the transaction. Of course, the problem with proof of stake ledgers is people can always lose their keys, and you can end up with arbitrary numbers of forged forks of blockchains. And some people are trying to address that problem in Ethereum using verifiable delay functions. And so we're just kind of punting the hardness of that problem out a little bit. But let's assume that we can do this thing. We can put things onto a ledger and we can get a proof of publication. By the way, when is my expiration time here? I should just to keep me honest.
So within the next 10 minutes. So
Good. Okay. Perfect. I will do that. Good. Okay. So at the end of the day, this is very simple, right? The observation here is once we have this tool, this very simple tool, which is a proof of publication blockchain, we can do a lot of things that are very powerful. And this observation seems very simple, but it lets you do an enormous number of things. The basic idea is, let's say that we want to keep state here. We have a blockchain where we can post some string S onto the blockchain, and we, in the simplest possible case, can then download a full copy of the ledger that is verifiable, meaning there is a proof of some kind that I can use to convince any verifier that the ledger is a valid ledger that, you know, I really submitted this string S to. And this covers, you know, most blockchains in real life, including proof of work blockchains under an economic assumption. Now, obviously, downloading the full ledger is annoying. It would be nice if we didn't have to do that, but this is just a simplifying assumption. And so what we can do basically now is we can build a system in which, let's imagine that we have an adversarial user, an adversarial host who is trying to do, you know, trying to run a secure TEE, but is not trustworthy enough to keep state. And let's assume that the secure computing device, the TEE itself, can't keep state internally because it's completely software based and doesn't have any hardware counters, and so can always be rolled back. What we can do now, and there's many different configurations of this, but one configuration is we can basically have the user, and who is in this case also the host, provide their input either in plain text or in a committed form onto a publicly verifiable ledger. And then they can download that ledger saying, look, I've actually done this. I've placed my input there. It may be private and committed, and they get this ledger as well as the proof that this has been done. And once they've done that, they can now basically provide their input to the secure computing device along with a copy of the ledger and the proof. And this basically creates kind of it's essentially just a commit reveal that allows you to now prove that you've placed this thing on there. And what I'm not showing here is that we do have the problem of state. So how do you deal with state? And I may have actually forgotten the slide that shows what you do with state. But the beautiful thing about this is that the secure computing device can now output a commitment to its current state, and it can require that you basically post that commitment to the current state onto the blockchain and show that there is on the blockchain a series of update rules that allow you to basically move from state to state. So essentially we can outsource state keeping to this very powerful blockchain tool. And there's a full protocol that we have in a paper, and other people have replicated this in other protocols specifically. I think I actually have like a piece of the protocol, but I'm really just trying to kind of do this very quickly. So we have this ability to basically outsource state to arbitrary blockchains in a way that's private. And this turns out to be very nice and very useful. We can also use this for trusted input output, right? So once we have a proof of publication, it's fairly trivial to basically use the blockchain to output useful information in a way that we can't censor. And when I say we can't censor it, what I mean is, of course, the host can censor anything. The host can block any output from a TEE. But what will happen in this case is we can condition the continued future execution of that TEE on receiving a proof that a particular value was published. So a TEE can basically say, here's some data, post it to the blockchain, come back to me with a proof that this data was published on the blockchain, and I'll keep letting you do stuff. Otherwise, good luck, you're not going to be able to access me anymore. And so we can also do that. And this also allows us to use the blockchain basically as a trusted source of both output and publication and a trusted source of input. So let me give you one last sort of concrete example of this. Let's say that I want to log every time somebody tries to access a resource inside of a TEE. I can make it so that the only way to initiate that access is to post some kind of log that says you did this thing on chain. And so now we have the ability to force logging. Of course, the user can block that logging, but then they won't be able to access the resource. So it allows us to do a number of things that we can't normally do with a standard TE as well. And what's really cool about this, and it's only a 30-minute talk, but I really want to point to some other people's kind of interesting research, is it turns out that with a lot of assumptions and the use of either witness encryption or obfuscation and some other tools, the blockchain itself, with these basic ideas of doing state keeping and posting things, allows us to implement really things that are impossible to build using pure cryptography. So we can implement, for example, one-time programs. We're using obfuscation on the blockchain. We can implement non-interactive MPC, which is fundamentally impossible even if we have cryptographic obfuscation. We can store and retrieve secrets on a blockchain using only cryptography. And of course, using TEEs, we can also verifiably store and retrieve secrets. And of course, there are a number of people who've done practical things, including Mick, and as well as platforms like Ekiden and Oasis, which actually use these similar ideas for state keeping. And so this stuff is out there. Two things that we've done with this, we've shown basically a general transform that lets you add state using blockchains. And one of the things that I think is really exciting, although nobody else cares about this, is we can use TEEs and blockchains without state to achieve fairness in multi-party computation protocols. So in other words, if we have two parties and one party aborts the protocol early, it gives us kind of a new set of techniques that we can use to avoid problems. And I think this is an exciting thing. And so I just want to end with, where I would like to see this research go. And this research is continuing to go, but I would really like to see people out in the real world use these techniques to harden existing systems, kind of like the way Mick mentioned, right? So today we're mostly using TEs to kind of do stuff that helps with blockchains, but I'd love to see people taking, for example, custody solutions and making it so that if somebody tries to hack into my TE-based key storage solution, they can't do that unless they post something on a blockchain, which at least provides logging and provides some kind of ability to condition access. So I think that would be very interesting. And I would also like to see, and we've done some research on this, there are a number of people who are proposing to build key escrow systems where, governments can access your encrypted messages. And one possible future solution to building these systems is that I don't want to build these systems, but if we must, blockchains and powerful TE tools or obfuscation allow us to build systems where governments are constrained. In other words, they must post a proof that they need to access a piece of data according to some predicate. And then once they can only access that data once they've posted that proof. And the benefit of this is if somebody steals your decryption key, they still can't decrypt invisibly. There is now a way to make it so that even the theft of a confidentiality key means that there has to be some visible public posting as part of the decryption process. So this allows us to turn these undetectable confidentiality breaks maybe into more detectable breaks. And that's kind of, I think, an interesting area that may or may not have more work to be done in it. So I would love to see people doing that. I think I've reached the end of my time. And so that's pretty much it. Thank you.
Thanks a lot, Matt. So we'll open the floor for questions.
So there is a question from anonymous attendee. Yeah.
Sorry, I didn't hear that.
There is a question on the chat window.
Oh, okay. Sorry.
So I think maybe I'll read it out aloud. So if we had the chance to develop the system from scratch instead of relying on blockchains for public storage, how would you go about it?
If I had to build the system from scratch, well, we've seen a bunch of people building these systems, right? So for example, Signal SVR uses Raft consensus, and they build their own consensus network running directly. Oh God. And like, I don't know how many pieces of it run inside of the enclave and how many pieces run outside. To me, this seems very, it's a lot of work. It's a lot of extra complexity that you're adding into the enclave. And it would really be nice to see that not running inside the enclave, or at least, separate enclaves. And so for me, if I had to build it from scratch, there are a lot of things I would do. But what I would really do is I would build a consensus system that is really, really scalable. And it's possible to take these kind of commit reveal type and publication messages from other enclaves and place them online directly. And of course, people are probably working on this as we speak, but I would love to see more people building really high throughput, very low latency systems that can handle that kind of commit reveal type of publication and so on.
So I think, so if I were to summarize, I think what you said, I will essentially build a blockchain if I did not have access to a blockchain.
I mean, that's what people are doing, right? At the end of the day, everybody who has sort of proposed to solve this consensus problem outside of like data centers is building a consensus system. They're just building a private consensus system. And I think that's maybe good in some sense, but like we should have really good, global, very scalable live systems that work very well. And we should reuse those systems rather than building a million new little chains.
Makes sense. So we are already at 1, but if there's one more question, we can take it.
Yeah. So if Matt, turn this around for a minute, right? What would you like from the TEE that would actually help you do state consensus and serialization and make it easier? I mean, we can't make the host trustworthy, right? That part's not going to happen. But the monotonic counters was an interesting approach, and I have a love-hate relationship with monotonic counters, but what would you want from a TEE to make it easier to do this sort of state synchronization?
Yeah, I mean, actually, monotonic counters is really, I advise a company that's doing custody right now, and they're working on the various different systems. And like the biggest problem that always comes up is state keeping. It is a huge hole in all of these systems. And SGX removing state keeping at all is really hard and bad, and nobody's quite sure what they're going to do about it. So like for me, counters worked really well. I understand the limitations of it, but it worked really well. And I don't have an alternative to it other than using these outside systems. But that is the thing I would want the most. And by the way, I would want that as a kind of an enclave service, right? Like you already have this like sealing enclave and you have all these other things. I would want that to be provided to me as a service rather than me having to build it from scratch.
Thanks, Matt. So Andy, did you have a question, or? I saw your hand up. You're muted.
All right, how about now? Okay, all right, sorry to take up so much time. I wondered if you would, is there like a design principle, like say you're choosing between using zero knowledge proofs in some, wacky new design or using TEEs as kind of one, I would think you would say that even snarks are kind of footgun prone, but perhaps better than TEEs. If you could use snarks, use them instead of TEEs.
Yeah, I mean, I think at the end of the day, right, like you have to think very hard about your adversary. If your adversary is like the global adversary trying to attack a blockchain network, then like TEEs are not going to be enough, right? But if your adversary is like, hey, I'm trying to do some kind of privacy preserving computation with one other person, and I just want to make sure that like I'm not stealing their data, I think that's a situation. So yeah, there should be a good design principle, but I think right now those are the heuristics I would use.
Thanks.
All right. Thanks a lot, Matt, for your talk. We'll move on to the last talk of the day. This is by Jonathan Passerat-Pambach. I'm sorry if I'm not pronouncing your name correctly. And he's a senior researcher at Flashbots, and he'll talk about privacy, cross-MEV, mitigation, collaboration, and decentralization. Over to you, Jonathan.
Thank you. Can you guys hear me well? And can you see the slides move? Because
Yes.
Yeah, perfect. Okay, cool. All right. So today I want to tell you a bit of like what is MEV first to give an intro to the audience, and to see how Flashbots has been trying to address the MEV problem, and in particular, how do we use or plan to use privacy techniques, and in particular TEs to address this issue. So first of all, for those not familiar with the issue, what is MEV? It's the acronym for maximal extractable value. So in short, it's the profit a miner or any kind of like validator, any organizer of transactions in a blockchain network. It's the profit this actor can make by reorganizing the order of transactions. So inserting their own transactions, censoring transactions, changing orders, all these kind of like things that ultimately compose the block. And in practice, I want to show you how it can happen. First, with a non-DeFi example, for those not familiar with like financial primitives. So I guess you'll remember these CryptoKitties. There was part of the game that consisted in like breeding new kittens. And the way you would do that, you would first issue a breeding transaction as the owner of these kitties. And then the smart contract would have you wait for a certain period of time, a delay. And once this delay was elapsed, you would have to send a second transaction to trigger the birth of the new kitty, and you could claim a reward based on this new kitty generation. So what's the issue here? Well, basically, you as the user, like you send your second transaction to claim the reward for your new kitty, and you assign like some priority that you express in terms of gas on Ethereum, for example. However, there's an attacker on the network that sees your transaction in the public mempool because it's for everyone to see, and this attacker spots that by simulating this transaction and replacing your address with his, he notices that it increases his balance by executing this transaction. So what does it do is that it copies your transaction and just replaces the gas price you're paying to make sure that his copy of the transaction becomes more of higher priority than yours. What happens normally is that the miner or the validator will pick this transaction because it like provides higher gas fees. So the attacker will steal the reward. So that's already bad. But what will happen is that you as the originator of the transaction, you will still pay part of the gas for part of the execution of your transaction up until it reverts because the kitty has already been birthed. So you don't get your reward and you get a financial penalty on top. So it's not very nice as an end user. What is even more worrying is that we've seen these attacks become more and more prevalent on decentralized exchanges. In particular, there's like one that is pretty frustrating for users, where you try to purchase an asset on the decentralized exchange, as you express your intent to buy these assets by swapping a specific cryptocurrency for another that is paired with it. And one of these attackers, one of these bots, again sees your transaction and places the same buy transaction, but with a slightly higher priority. So it will get the same token that you're trying to purchase, but before you. And what happens then is that you, because you allowed for what we call some slippage in the price you're willing to pay, will always get the worst price that you were ready to pay for this token. So the attacker, by purchasing before you, pushes the price in the worst conditions. and then basically he can sell these assets back afterwards to make sure that he generates some profit. So why is that an issue? Well, first of all, the main takeaway of these two examples is that we know now that these what we call front-running bots are actually generalized. So what I mean by that is that it doesn't matter what decentralized application you're targeting with your transactions. If a bot can detect that by executing the same transaction, if they can benefit, you will be front-run. And there's a whole story, scary story around it that has been written on the Paradigm blog that I highly recommend you reading. That uses like the Dark Forest sci-fi book as an analogy that I also recommend for you to read. How did we, started to speak about these as being like MEV, and why is it even more of a problem than just for end users? Well, it started with the paper by Phil Diane et al. From 2019 that was called Flashboys 2.0. And what this paper shows, among many other things, was that bots were actually competing with each other to front-run users and to claim the rewards of these transactions. And the way they were competing against each other was by observing the mempool to see if their transaction was still the one paying the most gas, and thus being the one that would have higher priority and would be included on chain and would claim the opportunity. So they were engaging in what the paper describes as programmable gas auctions, PGAs, to keep on outbidding each other until one of the transactions was included by a miner in a block. So on top of like all the issues we've seen for end users, what that creates is that it impacts the peer-to-peer layer of the network. It creates network congestion because there's lots of transactions being sent and propagated on the network that in the end won't even be included. And more worryingly, the competition for accessing these MEV opportunities can lead to consensus security instabilities on the L1 level, because by creating an incentive and a competition to access MEV, the paper shows that there is an incentive for the block builders, for the miners, to sometimes reorganize the transaction in such a way that they can even go back in the chain in what they label as like time-bended attacks, but also to set up permission communication infrastructure between these elaborate traders and the miners themselves. So it threatens the neutrality, the transparency, and the decentralization of the network as a whole. So beyond that, this paper was originally tackling and showing these problems in proof of work Ethereum, but the problem becomes even more prevalent with proof of stake Ethereum, because with lower block rewards, the relative importance of the MEV you can extract from a block increases. So there is a risk that it creates a self-reinforcing loop where the ultimate validators that include transactions and that include blocks on chain are incentivized to get more and more MEV. And that's bad, because by doing that, you create a centralization driver around these validators. So we absolutely don't want that to happen. And interesting, like there's multiple approaches to try and address this MEV issue. At Flashbots, we mostly focus on the application layer, but for example, Ethereum Foundation studies MEV at the consensus layer. Just to be sure we are on the same page with that, we actually think that not all MEV is bad. So there is some bad MEV, as you've seen, like with the sandwiches, for example. But some of it can have positive externalities. So, for example, arbitraging between different decentralized exchanges to rebalance the prices can be seen as being like a positive externality, for example. So how does Flashbot solve this issue in the first place, or actually try to solve the issue? Well, there is something that we call the Flashbots auction, which is basically a series of free and open source software that have been released, starting from a piece of software called MEV-Geth, which was a fork of the Geth client, but also a series of services that we call the relays, and more recently MEV-Boost and MEV-Share. To give you a better idea of like all these new terms that we've introduced, these new actors in the system, the idea is to isolate a specific actor called the searcher that specializes in finding these MEV opportunities. Because we consider that, as we've seen, not all MEV is bad. So we want to mitigate the bad MEV, but we also want to make sure that as many people as possible can have access to the good MEV. And these searchers that specialize in like finding MEV, they compete against each other to find the most profitable opportunities by observing the mempool and bundling transactions together in what we call a bundle. They send these bundles before to the miners and now to validators. So we first see that there is a communication and essentially like a trust component between searchers and validators, because validators ultimately include blocks and thus MEV opportunities on chain, but searchers have done the hard work of like identifying these opportunities, and they want to make sure that they will be the ones benefiting from it at the end of the day. One thing to note is that these bundles do address the issue of like spamming the network with the programmable gas auctions, in the sense that searchers can now simulate bundles before sending them, and they have an incentive to simulate only good bundles because that's how they will be paid. But also the bundles introduce the notion of like a direct payment to the miners instead of like paying by a gas price. So the payment becomes conditioned to the transaction success. So you don't pay fees anymore when transaction revert, for example. And with the simulation, you avoid sending like bundles that won't be included. In terms of like how does that work in practice and how it's organized? So as I said, like in the previous proof of work Ethereum, we had this fork of the Geth client that was just basically adding a new RPC call to the client, so that miners could run that fork and open this RPC for searchers to send them bundles. And we have ultimately like a privacy gain by just doing that, because these create like a direct line of communication with the miners. So these transactions and the bundles, they don't transit through the public mempool anymore. Interestingly, that removes the PGA, and you could say, well, but doesn't it focus too much on the right part of the ecosystem, so the searchers and the miners, but leaves out the user that we want to protect as well in the end? Well, not really, because users can send single transaction bundles. So it would seem that we have a solution for proof of work Ethereum, but as you know, the merge has happened since. We needed like a different solution to that, and this different solution comes in the shape of a concept called Propser Builder Separation, PBS. Why do we want to separate Propsers and builders? So we've seen that the actors with a lot of power in the network were validators, and there was a risk that validators were getting centralized if their task was becoming more and more complicated and thus specialized. So the goal of this specification and the way to handle transactions and block building in proof of stake Ethereum was to, in a way, accept the fact that there would be centralized actors, but in that case, that would be the block builders. And we agree that block builders would be able to absorb economies of scales and thus centralize more and more by getting more and more specialized. And that's what we see today, because I think there's like basically 5 block builders building most of the blocks on Ethereum. But the trade-off is that by separating the construction of the block to proposing the block to the chain for inclusion, which remains the role of the validators only, we simplify the task of the validators. They just have to accept the highest bid, the block containing the most MEV, for example, provided by the block builders. So that the task remains simple, and as such, validators can remain decentralized. So that's what we've been building with MEV-Boost. It's an implementation of this concept, and you see the different block builders interacting with the searchers. And block building also becomes a competitive market. It's not just searchers competing against each other. It's also block builders fighting one another to propose the best block to this actor that we call the relay. And now you start to see potentially a problem, because this relay actor is basically here to make sure that validators will actually publish the block that block builders are creating. But at the same time, block builders want the guarantee that validators want the guarantee that they will get an actual block from block builders. Otherwise, they would get flashed if their turns come to propose a block and they don't have anything to show to the network. So we need these relays to act as a trusted entity between these 2 actors that have separate interests. So where we are now in this state of things is that we have a way to guarantee the decentralization of validators, but we still have like this driving centralization force around builders, and we have this strong trust in relays across the network. So it's not really ideal. And at the same time, we've kind of left the users out of the equation, because yes, they get pre-trade privacy, but they don't really benefit from MEV, from the MEV that transaction generate. And the question is, can privacy and TE technologies help addressing these issues I've just mentioned? Sorry. And the way we see that, the way we design the system is that I'm very sorry. Is that we delineate like all these interactions along something that we call the transaction supply chain. So you can think of it as like all the interaction points that we have between actors in the system. And by the way, it's like according to Flashbot, it's not something that is proposed by the whole Ethereum community. It's just the way we represent things. And what we want to work on and what we want to apply TEs and privacy techs on is at each of these interfaces between the actors involved in the game. So, for instance, when we consider the interface between users and searchers, what do each want? Like users want pre-trade privacy, and searchers, they want guarantees that the strategies they apply to find the MEV opportunities will remain confidential. They consider that to be a protected IP that they've like spent a lot of money to generate. So they want this guarantee. And at the moment, they trust centralized entities like Flashbots to give them these guarantees. And we have like these kind of dynamics all the way through the supply chain between searchers and builders, and between builders and validators, as we've seen. So another way to to represent this supply chain is to also consider what is being exchanged, what is the medium of communication between each of these actors. Is that a transaction? Then it turns into a bundle, a block, and a block that is being published. And from our work roadmap, the way we slice things is that we consider like each of the separate problems as opposed to tackling the whole transaction supply chain as a whole, for the simple reason that it can be pretty difficult to reason about. So most of the things I'm gonna show you are just focusing on like specific parts of the transaction supply chain. And in particular, we've been working on two things lately, on proposing like a prototype MPC approach to address the trust balance at the user searcher interface, but also using SGX to address like the searcher builder interface. So starting with that, we have recently released an article showing how we've been able to run a full Geth node within SGX. So it's using the Grameen libOS. So we of course know that it's not perfect and it's not fully secure, but it's still a first achievement. This node, this block builder, is actually running right now and building blocks on the Ethereum mainnet. And you can find the source code and the documentation on our website. And interestingly, like there remains quite a lot of challenges around making this builder more robust. So first of all, there's of course like the hardware requirements that require like the latest generations of SGX. But there's also a few very interesting like R&D problems that we've hit along the way. Basically, the idea to provide reproducible builds of the whole stack, including Grameen plus the Geth node, but also, of course, the performance. Because as we've seen, block building is a competitive market. So the fact that the block builder runs within SGX and as such like provides more confidentiality to the actors in the network is not enough to guarantee that it's going to be used and it's going to be competitive in the market. So we need to bring the performance as close as possible to running a block builder with outside of SGX, basically. And importantly, we've got when you consider decentralization, in our case, like we want to be sure that anyone could technically run our infrastructure, our code. And as such, it becomes pretty challenging to guarantee that there won't be any side channels being exploited by the node operator in that case. And if you flip the problem around, if you remember, I was mentioning that the searchers were considering that the strategies that they're employing was basically IP and was also very confidential data. So if we allow for decentralization, and you imagine that, for example, searchers or there's an enclave, an SGX enclave running that allows searchers to have access to encrypted transactions from the users. The thing is that we can't package the searcher strategy within the SGX enclave. So what I mean by that is that we can't verify that what the SGX enclave is running entirely. We can only verify that there's a certain empty shell, but there will always remain part of the code that is running within the SGX that is the property of the searchers, and that we can't really audit. And by doing that, what happened is that we expose the system not to side channels anymore, but to covert channels that the searchers could themselves exploit from within the enclave to leak secrets over time. So that's something we're still trying to quantify and to qualify to see how much of an issue it is. And basically, when considering this strategy, it's really about, for us, what is the trade-off, because we know there's going to be a trade-off between the level of privacy that we can provide to the end users and the efficiency that we can guarantee to make sure that the actors remain competitive in the market. As an alternative to this design, we've been trying to address this issue of covered channels by rewriting a specific searcher opportunity that we call the backgrounds using a three-party MPC protocol. And by doing that, by integrating not only the users and the searcher in the MPC, but also the block builder, you remove the opportunity for covered channels, because we assume that basically the searcher is not going to get any feedback from what is running in his strategy. The output of the MPC will directly be in the hands of the block builder. So quite a lot of challenges here as well. Of course, it's not as fast as running within SGX. So we are at the moment exploring like multiple directions, for example, combining this approach with some form of homomorphic encryption to reduce the communication at the MPC level. But we also want to explore, combining SGX and MPC to see again how we can accelerate generic protocols. And in that case, it could be potentially like worth revisiting designs like the CCF framework that we've heard about before. A few more directions, things that we want to explore, and I label that as a call to action, because Flashbots is a very open research initiative. So if you want to collaborate with us, if you think that is interesting, or if you want to learn more because you want to potentially contribute, please do tell us. And I hope you'll find these problems interesting. So 4 research directions we want to explore. The first one, and we've been talking about it a lot during the panel, is to try and strengthen TEs as much as we can. So we want to, we've committed to use TEs for the foreseeable future as part of a roadmap. And it's interesting to understand, why do TEs break? So the conversation before between Matt and Nick was pretty relevant, I think. To me, it's interesting to see if there's design flows we could avoid by exploring alternatives to SGX maybe. Study also how to best handle these side channels and these covered channels. So the obvious answer is to look into Oblivious algorithm or RAM, but we know that it's gonna increase the overhead even further. And since it remains a competitive market, there will again be a trade-off to make between privacy and efficiency. Another thing that we are exploring as well is this notion of running a heterogeneous network of TEs. So a lot of benefits of doing that for the sake of decentralization. And by decentralization, what I mean is both geographic decentralization, but also decentralizing maybe too powerful stakeholders. If we just run Intel hardware, what would be the impact, for example, if we end up like securing very important financial transactions, but also just simply like letting users, letting them be free to choose the hardware they want to run. And as we've seen, we don't really have like a framework to think about the threat model of this kind of heterogeneous networks of TEs. We've also seen that they all provide some kind of remote attestation, but that might take different forms and provide different guarantees ultimately if you go from one vendor to another. So that is something that we are very interested in collaborating upon to even from the start trying to run a heterogeneous network of the commercially available TEs as of today, for instance. Another line of work that we are following very closely is what we label as encrypted mempools. So there's a bunch of approaches that are alternatives to Flashbots that start from the thesis that if you encrypt everything, you prevent all of the MEV, and thus you reach a better state. So our thesis is different. as I said, we want to prevent the bad MEV and democratize the good one, because we think the economic efficiency is greater in this model. That being said, there is a lot to learn on how to design these encrypted mempools, and even though we want to enable operations on the encrypted transactions that will go in our encrypted mempool, there will be, of course, like common design patterns between the two of them. So studying encrypted mempools and threshold cryptography in general is high priority as well on our roadmap. And the final one,
we are already a couple of minutes over.
oh, sorry, I've just got one slide left. So basically, that's the one. I'll just say a word on that one. That's there's like a few references to that one. Distributed block building. It's trying to remove the centralization from the builders as well, because we've seen that Validators was sold by PBS. And I'll just leave the summary slide to allow you to ask any question if you have any.
All right. Thanks a lot, Jonathan. So I think in the interest of time, maybe we will just take one question. There's someone. Andrew, do you want to go ahead?
Yeah, okay. Hey, thanks, Jonathan. So, something struck me with your Gramian experiment that, talking about the, what it's good for, what it can, be used, or how someone could chip in. It struck me that one of the consequences of those expensive startups is that it's difficult to say, know how to attack it, or, what it would take to demonstrate the side channels for it. So I wondered if one way to take that is maybe to make like a good challenge case, something that's sort of like designed to be as easy to attack as possible, if there's, a side channel to demonstrate on it.
Absolutely. I totally agree. And I think, like, for example, if you think about the way I've handled the presentation, there's a lot of intro material that, shouldn't be the case if we had a very nice framework, for example, for all the SNP researchers to come and play without having to download like a whole of the whole background on MEV before they can experiment with. So yeah, totally agree. If we make it simpler, it would be great to start throwing around like security challenges and bounties.
Thanks.
All right. Thanks a lot, Jonathan. So with that, we're concluding day one. So thanks a lot all the speakers, and thanks a lot all the attendees for joining in and engaging in interesting discussions. So tomorrow we have 4 talks and under panel. So we have Nick from Oasis Labs, Andrew from UIUC, Itai Eyal from Technion, and Guy Zeiskin from Secret Network presenting talks. So we look forward to seeing you tomorrow at the same time. Thanks, everyone.